Aunque
Sí, caldera. En octubre. Okay, guys, we're going to start. Thanks for making it to the last day of the workshop. Our final keynote speaker is Adrián Pérez Salinas. He did his PhD at the Barcelona Supercomputing Center under the supervision of Artur García Sáez and José La Torre. And now he has moved to the Lorentz Institute in Leiden for a postdoc. Despite his still short career, he's an expert on quantum computing and quantum machine learning. He has one of the seminal papers in quantum machine learning titled Data Reuploading for a Universal Quantum Classifier, which I'm sure some, if not many of you will have read. And I'm sure he'll cover some of the main ideas of the paper today because he's going to talk about quantum machine learning. So whenever you want, Adrian.
Thank you. Good morning. Thank you for coming, you brave, you heroes. I know that some of you were already very late yesterday in this place. It's a big pleasure to be here. Thank you very much. I know it might seem like something that everybody says, but when I was a high school student, I came here for one of my first science talks ever as attendee and not as a speaker, obviously. And since then, I always wanted to come back because I'm from here. I'm from the city, and I like to come back to the roots. So today we'll be speaking about quantum machine learning, and I will be covering some of the works that I've done, but also some other works that some other people has done. And my goal here is not that. Okay, it's not that anyone can come out of this room knowing everything about quantum machine learning, but rather being more or less familiar with the kind of concepts that are important in this field. I don't want to go into proofs. I don't want to go into heavy maths, but I would like you to. I would like to deliver the way of thinking that we need to have in order to do research and have proper conversations on this topic. So it's a kind of short presentation, but please feel free to interrupt. I'd rather not cover it all than cover things badly. Right? So this is a little bit of the outline that I'm going to cover. For sure, the most important part is here. If we arrive to the coffee break here and you understand everything, I'm still happy, right? Everything else is a state of the art and things and things that one needs to learn if you want to work on that. But really, the mindset is established here. So please, even more here, stop me every time you don't understand anything or every time there is any comment or any question. We'll be talking first about the rudiments of how machine learning works, and then we will be covering several steps in variational quantum machine learning, which is what I've worked mainly on, then kernel-based quantum machine learning, linear algebra-based, and finally generative models. Note that there is a increment in near-term quantum computing towards fault-tolerant quantum computing, even though nowadays quantum advantage is not super clear. And finally, we will be covering this learning quantum versus classical data, because there are some people that think, including me, or that used to think that it's important to use quantum computers for classical machine learning, say for learning data. But what happens when quantum data comes into the game? That is a very interesting topic. So let us go with it. So, is there anyone here that is already familiar or not? Well, that is not familiar, broadly speaking, with the concept of machine learning? Okay. So, machine learning is a set of techniques that we have developed in full generality, not necessarily quantum, not necessarily classical. Is a collection of techniques that we have developed so that we can program the computer without explicitly program them. It's one of the most famous examples through history is whenever IBM developed this. I don't remember the name of the machine, but this machine that could beat the current champion the current chess champion of the world. And the entire thing is well, how to program a computer so that they can solve a problem in such a way that we don't even know what the machine is doing, right? And there are many techniques in this case. One can more or less classify the tasks to be solved with a machine learning algorithm as supervised learning, which is usually classification or regression, as unsupervised learning, which is classification but without having any references, reinforcement learning, which is some sort of you let the machine explore and get rewards so that you can find an optimal solution to a problem, in particular playing chess, for example, and generative modeling, which you have probably seen already by ChatGPT, DALI, and all this machinery that creates images, texts, and everything. There is a web page called This X Does Not Exist, and it can generate almost everything. So in this talk, we will focus primarily here, and the reason is because it's the simplest way of thinking of machine learning. Everything else you can also do it, but it adds up some problems and some difficulties that are not trivial, and I really think it's not worth it at this level. So what is the main thing that makes machine learning different from any other kind of programming a computer is data. Data plays a fundamental role in every machine learning algorithm or every machine learning procedure because data is everything you have. You learn by example. You cannot tell the machine, do these steps, and then you will arrive to a solution because even if that exists, you probably don't know what the solution is. I don't know how to play chess, but I know how to program a computer to learn, for the computer to learn how to play chess. And everything comes from data. But data, you have to be very careful with it because if misinterpreted, then it can lead to very, very wrong conclusions. And a very famous example is this one. So this is a story, maybe some of you know, about some statisticians in the Second World War thinking, well, it's happening that all my planes are coming back with a lot of holes from the bullets of the other planes. So what can I do to reduce the damage of the on the planes? And they draw where they received a shot. And this is the drawing. So what would everyone do? What would do? Cover this part, cover this part, cover this part, cover this part. Put some sort of a plank of steel so that it's more resistant, and that's it. Well, no. The obvious reason is obvious once you see it is if you get a bullet here, you can come back. If you get a bullet here, you cannot come back. Therefore, this data, which is not the important one, is not seen because of the survival bias. This kind of behavior of data you have to really take into account, and that will be very, very, very important whenever you introduce data into any sort of algorithm, especially in quantum. So I would like to cover first a couple of relevant concepts in machine learning. So the first one is going to be the training. As I'm saying, we are learning by example. So the only thing that we can have is to have a model such that you show this data to the model, and the model in some way or another learns what is the supplying structure of the data. If this data is very, very well structured and the machine learning is well done, then you will find a model such that whenever you input a new set of data, the solution that this model output is very close to reality. How is this done? Well, long story short, we have some model F that depends on a series of parameters, theta, and the only thing that we are doing is optimizing over this set of parameters. So we have some loss function that is normally defined as some average over the data of some distance between the output of the model and the data, so the reality, and we minimize that. In which cases is a model trainable? A model is trainable if it's efficient to find a good solution within the capabilities of the model. This is important. I would like to highlight this difference. Within the capabilities of the model. That means if I have a model and I can explore which is the optimal solution in that model, this is trainable. This does not mean that the model is good. The model can be absolutely terrible, but it's still trainable. It's not expressive, as we will see later. But I would like to highlight this. Second concept is about generalization. So we would like a computer to learn the underlying structure of data. We don't want the computer to learn the data by heart. It's not a memory thing. It's a abstract way of thinking. This is captured by generalization. So we would like, ideally, to have some model such that whenever I input some data that comes from some probability distribution, from some space of data, then the model outputs the correct solution or something close to the correct solution. But we don't have access to this. We don't have access to this because it might have infinitely many points, and we cannot train any model with infinitely many points. So what can we do? The only thing we can do is sample data from there. So what we would like is, if some model generalizes well, that means that by looking at this small set of data, then it can infer the structure of everything here. This is something that is known as the generalization or as the risk, and a way of understanding is that there is a trade-off between how well you train and how well you can generalize. Because if you train very well, then that means that the model has learned all the data by heart, but everything else is kind of random. If you train bad, then that means that wherever the new data is, it cannot be much worse than the training that we have already seen. Yes. Ooh, interesting question. Okay, efficient means that it grows. So the cost of finding the optimal, or the cost of finding a good minimum, scales at most polynomially with the size of the model. So this stems from computational complexity theory. In computational complexity, there are several classes, right? So there is P, MP, and so on, and you go by some exponential ladder. So if something, if solving one problem takes logarithmic number of steps in the size of a problem, that is super efficient. Polynomial is efficient. Exponential is not efficient. The boundary is there. So efficient is something that is at most polynomial with any degree. Yeah, because this scales asymptotically. That being said, I understand that from a practical point of view, a polynomial with a very high degree can be, in practice, worse than an exponential with a very small scale parameter. But let's say that from a theoretical point of view, efficient is polynomial in the number of polynomial in the size of the problem. Okay. So generalization is about this trade-off between how much you train and how much the model can infer from what it's saying. Next thing is expressivity. So a model is expressive if it can give a solution, an accurate approximation to a family of functions that correspond to the problem that we want to learn. That does not mean that it's trainable. Again, there are two different concepts, and it can be that a model can be very expressive but very hard to train, and the other way around. And in particular, in variational quantum algorithms, this happens a lot. So an example for expressivity is, imagine that my machine learning model is capable of is capable of representing any function of this kind, right? So if L grows infinitely, I could be capable of representing any odd function, but I will never be capable of representing their cosine or x squared, because it is just not in the pool of things that I can, in the pool of functions that I can represent. So yeah, it could be trainable. But what for? And finally, and this is something that is exclusive to quantum machine learning, is the dequantizability of the model. So dequantizability means that a model is dequantizable, a quantum machine learning model is dequantizable if there is some other model, some other classical model, such that such that the performance to solve a given task is similar. And this is an important question. This is an important concept, because it is not about simulability of quantum computers, what one could think, or it's not about finding the solution, finding the output of a given quantum computers. It's something a little bit more subtle, because a quantum machine learning algorithm could be non-simulable principle, because it's a very complicated model, and it's a very deep circuit with bad connectivity, and that implies that it's not simulable. But the output is something that I can handle easily with a classical computer. Therefore, I don't need to go through the hard path. I can go through the easy path. That means that the quantizability is a harder requirement than simulation. Harder in the sense that it's for me harder to prove that quantum machine learning is useful. It's very difficult to make statements in the sense of the quantizability, because classical models work very well, and we don't really know why. Because if you have worked with neural networks from a theoretical point of view, neural networks are a miracle. They are very expressive, we know that, but they are very hard to train. Or theoretically, they are very hard to train. They are even empty hard to train a neural network, and it still works. And we don't really know why. We have some trade-off between expressivity and generalization, and it turns out that neural networks can be very well trained and still generalize very well because of machinery inside. So it's a little bit of a miracle, and we don't really know why it works. And finally, statements of the quantization usually rely on specific problems that are believed to be BQP. I don't want to be close to I don't want to get into computational complexity again, but just BQP is problems that can be solved with a quantum computer, not with a classical computer. Any question of these concepts? Because now we are going to wrap them up. Okay. So this is part of one of my last works. So we have been thinking in this in these concepts and how they interplay with each other. So what would we like to do? So we have a set of different machine learning models. Some of them are non-quantum machine learning models. Some of them are non-dequantizable. Some of them are trainable. Some of them are variational. Some of them are useful. Whatever useful means, and that is something to be discussed with the in every case, right? And what we know is that, well, obviously there are some non-dequantizable models. There are some non-dequantizable and trainable models, but what we are missing is this, something that is mainly non-dequantizable and trainable, and also it has to generalize well, otherwise it's not a machine learning model. And you may have seen from several works that claim, or well, they don't claim, but the folklore around it claims that the models that are trainable are classically simulable and so on. Well, that is not always the case. And in all this scheme that you can find, I will explain now. I will there are a bit of the interplays here. So we can start from below. I was mentioning you that the quantization is related to simulability, but not the other way, but not tightly related. There is a small freedom there. So simulability implies the quantization if trainable, because, well, in particular, if I can simulate a quantum computer, I can simulate whatever it does for a quantum machine learning model, and that is obviously the quantizable, not the other way around, because I could come up with an alternative model. What else? So trainability, for example, does it imply? Sorry. Trainability does not imply in general that it can be gradient-based trainability, which is what we normally do with a neural network, because it's the cheapest and most robust way of training. But yes, the other way around for obvious reasons. Gradient-based trainability implies the absence of background plateaus or vanishing gradients, because if there is a vanishing gradient, it cannot be trainable with a gradient base, but not the other way around, because you can still have background plateaus and know where to look at. And finally, all this concept that were used to be, we used to believe that they are tightly related. In the community of quantum machine learning, it's much more subtle than expected. So the message to take home here is be very careful, very careful whenever you want to extrapolate. You want to extrapolate the knowledge of quantum computing and the knowledge of simulation and so on to data, because data changes the game. This is the take-home message of here. Any question? I know it's a little bit confusing. Yeah. Yes. Yes. So, okay. Imagine that I have a. Are you familiar with the Fourier picture? Okay. Fine. So what happened? Imagine that I have a model, right? And in this model, I introduce data using a unitary gate, which is exponential of some Hamiltonian times x. This Hamiltonian has an integer spectrum. Okay, fine. Then I do this, and then I have one encoding gate of this kind, one encoding gate of this kind, one encoding gate of this kind, and at the end, whatever I have, I'm going to have some function that can be written as a Fourier series. I mean, it's coefficient times exponential of I and x, right? Because they are integers, and then they kind of combine with each other. So how do these coefficients work? I have no clue. Absolutely no clue. And the reason is there is some algebraic structure inside the circuit that I don't know how it works. It's very complicated. And in general, if this is given by arbitrary quantum circuits, you cannot do that. You just cannot know what are the circuits. Sorry, you cannot know what are the outputs, simply because they are too complicated, and that clashes directly with theorems of simulability of quantum computing. But what you could do is, I don't know what are these coefficients, but I know that it's a Fourier function. So I can create a classical model that creates a Fourier function, a Fourier series, and then optimize the coefficients there in the classical model, not in the quantum model. That means that in the end, I have a quantum machine that gives me a Fourier series and a classical machine that gives me a Fourier series. I don't know how to map the Fourier series with each other, but if one performs well, the other has to perform well, because they are the same object, but obtained through different methods. But to me, that is the most intuitive example. Okay. Anything else? We're still in the introduction. Please feel free to interrupt. So, what we are going to discuss here is about quantum machines for learning classical data and quantum machines for learning quantum data. What we are not discussing is classical machine to learn about quantum data, but this is a super interesting topic. If you're interested in useful physics problems, you should take a look at this. So in quantum machines for learning classical data, data is produced in classical ways, obviously, and therefore it's easy to produce. And we use a quantum machine to learn the properties of that. What are the examples? Well, some variational algorithms, the ones that I've worked on, some discrete logarithm problem classification. Are you familiar with the discrete logarithm problem? Are you familiar with Shor? So everyone, so Shor rings a bell on everyone's head, right? So the discrete logarithm problem is the mathematical problem underlying Shor in a more general sense. So that means that Shor, some certain instances of phase estimation and so on, everything falls into the umbrella of discrete logarithm problem classification. I mention this because in the same sense that Shor is the only quantum algorithm that provides exponential advantage, a learning problem that stems from Shor or from this discrete logarithm problem version of Shor was the first one to prove exponential separation between classical and quantum machine learning algorithms. And finally, and it's in this paper, if you want to take a look, it's genius. My paper. Not once you see it, it's like obviously this is kind of trivial. It has to be like that, but you have to be there and see it. And finally, this linear algebra based machine learning, which are mainly based some way or another on the HHL algorithms or the HHL algorithm, which is just a fast way to invert matrices. In the case of quantum machine learning for learning quantum data is in quantum could be in a quantum form. Therefore, we don't have to load it, and therefore there is no overhead. But this data is very hard to create because it has an exponential overhead inside to create it. Or data is classical but extracted from a quantum source. So in principle, it's cheap to represent, but how can we create it? There is no way of doing it. Up to here the introduction. Again, if you have any question, please stop me. So, okay, I will move to the first item of the list, which is a variational quantum machine learning. So, in a nutshell, what is variational quantum computing? Variational quantum computers are hybrid models that combine a quantum computer that is controlled by a set of classical tunable parameters, and then we optimize these parameters however we can. In principle, this is useful because, well, nowadays computer have some limit in the qubit size, has some limit on depth, has some limit on noise, and what we expected is that through this optimization, we get to do something that is more efficient in any of those terms. Variational algorithms were in principle conceived as a way to overcome such limitations. For example, simplifying problems or saying, well, I can take a shortcut to a solution, or I can even mitigate errors. Something like, well, I know that I have a computer that my solution is given by a computation with a lot of layers, but maybe there is some other unitary operation which is cheaper in that sense and give me a reasonably good approximation. Then, since I don't know how to find it, I just optimize it. How do we do it? In general, is we create some parameterized quantum circuit, because see that depends on some parameters. However they are, we are not going into those details. And this ansatz can generate some output state that depends on data, that does not depend on data, that we'll see. The problem of interest is encoded in some Hamiltonian, and we measure the energy of this Hamiltonian. So the solution of the problem is somehow encoded into the ground state of this Hamiltonian. If we can find this, then that's it. And then we optimize classically the parameters of theta, the parameters theta, to minimize discrete functions. And notice that we can never, the best thing that we can reach is the optimal solution. There is nothing below for construction. This is a little bit of the scheme. If you're interested in all these variational quantum algorithms, this is my reference. Also written by a friend of us, Alba Cervera, who is a leader of the Quantum Spain, and well, manager. and this has a nice overview of everything that you would like to learn up to the date where it was published. And I think it was 2021. I would like to say here that there is a recurring joke in the community of variational quantum algorithms, which is we wanted to make these variational algorithms to somehow protect us against noise, give a solution that we cannot reach anyhow, and be trainable. And the last conversations that I had with some of the researchers of the world were something along the lines of, this is the worst intuition ever, because it turned out that most of these concepts, well, we just saw that they are not true. So usefulness of variational quantum algorithms, I kind of doubt of them, but they are definitely super interesting to understand what are the properties of quantum computer. Okay, in the case of variational quantum machine learning, what we're doing is introducing some data into the game. How can we do that? Well, it's kind of a natural extension. The only thing that we need to do is to load this data somehow. How could we do that? We could do it by saying, instead of having some input state that comes from the data, I am loading this data through some feature map, and through this feature map, that's it. From now on, everything is a variational quantum algorithm, and I can just optimize it. Fair. What is the problem here? So in machine learning in general, we don't know how to solve the problem. Because if we knew how to solve the problem, then we wouldn't need data for that. What is happening here is that I'm choosing arbitrarily, however I want, some way of encoding the data here, and then I measure, and then I optimize the measurement. Okay, fair enough. This measure can be super optimal. Perfect. If this is not capable of solving the problem, you're out of the game automatically. And if you know how to solve this problem, then this is not a quantum, then this is not a machine learning. This is just a standard problem. You just know how to solve it and give the recipe for that. But this is no machine learning. How can we do that? Well, we can optimize the feature map. And this is where learning happens. This is explicitly the moment where learning happens. And how can we do that? Well, you have to go into really what are the constructions of the feature map. Say, for example, this is this linear model, the first one without training the data. This is a paper that came out in 2018 and was a hit because of the experiments and so on. So what are we doing? We are encoding some map some data in particular through this feature map that is given by this circuit. Don't worry about the details. The only thing what we're doing is we have some data here and we're mapping it through a block sphere or through some sphere of higher dimensions. Don't really matters. So the best thing that we can do is to find this projector. We're just knowing where to measure, and by knowing how to measure, well, we just find an optimal projection. But it doesn't matter. It doesn't really matter what is the projection that we can do. We are upper bounded by the performance of the feature map. Say, for example, this particular example that comes from this paper. I don't know how to classify that. And you give me a set of points, and I don't know how to classify that. How is it possible? How is it possible that this paper in particular knows how to solve this problem? Well, there's a trick here. The trick is that the data was created with the same feature map that was used to classify. Therefore, it's a loophole. We are not going any farther. We are not learning anything. So how? If you give me some data that you don't know where it comes from, you have no idea, absolutely no idea of the structure that you have inside, how do you do it? Well, finding the feature maps. Feature map is the core ingredient of this task. And how we found a way to systematically find the feature maps is by this paper that Juan was mentioning, of this data reuploading. The idea is very simple. In a neural network, if you have worked with that, neural networks take some input data and transfers it to different neurons. But what is really happening is that we have some data, we're copying it as many times as we want, and just computing it to the next neurons. Well, cheap, because we are in a classical computer. But what happens in a quantum computer? We cannot copy data. So the no cloning theory, this is a very fundamental property. So what can we do it? Well, we cannot copy the quantum data, I agree. But no one is preventing me from copying classical data. So what I can do is copy classical data outside of the circuit and then introduce it in back. This is the entire idea. So we have some parameterized gates here. We have some parameterized gates. We have some data, and we are just interleaving them and optimizing these parameterized gates. By doing that, what we are really doing is optimizing the Fourier map. Sorry, optimizing the feature map. And that allows me or anyone using this model to create an output function in the quantum circuit that is universal in the data. That means I can fit anything. I can fit any continuous function or approximate any function. Certain constraints that stem from the obvious requirements from quantum computing, but that's it. This is universal. Now I'm learning. Now I can create a model that I don't know how it works, but it's learning. Because if I optimize the model, I just tell you, well, this is the data, find the parameters and however algorithm you want to, find the parameters that matches the data as good as possible. That's it. Then we are learning. And this was one of the first papers that gave the triggered all this field. The key point here is redundancy. We really need redundancy in the information. And this is something that we already knew from the neural networks, but we kind of had to know how to translate it from classical analysis to quantum analysis. This also admits a representation in the Fourier space that we were saying before. Depending on how you have the spectrum here, you will have different functions, different spectrum, and you can match different functions. So data reuploading. Okay. I lied to you a bit because I was telling you that the linear models could not optimize, were not learning anything, right? Because we're not learning anything because the feature map is already fixed, right? But and already fixed, and we can only find the optimal measurement. But it turns out that there is an equivalence between the data reuploading and the linear models. That means there exists a construction such that if I get a linear model with input that depends on data and just some operation that depends on parameters, with a feature map is kind of trivial, then what happens is that effectively it behaves like as a reuploading, and effectively it's a learning algorithm. What happens as well is that we have an overhead in we have an overhead in number of qubits, and we have an overhead in connectivity, right? So that means that both data reuploading and linear models are very similar, and they are also related to the kernel models that we will explore later. But the way of thinking of them is very different, and we really had to create a specific mapping from linear to reuploading so that they could match. How this is done? This is really very easy. What we are doing is we have some data that is encoded in the binary form, and by doing that, we just create some control operations. Those will depend on a series of parameters, right? And that's it. This effectively behaves as data dependent gates. That's it. End of the game. You have to take into account the errors. You have to take into account the approximations you have done, and in the end, you just measure here. End of the proof. Yeah. Fixed gate that are data dependent or independent. Okay. Well, I think that you're referring to standard variational quantum algorithms without data. No, the reason why you need these fixed gates is because you need to trigger entanglement. Entanglement. If you don't add these entangling gates, what is happening is that effectively you don't have a space of 2 to the n. You have the tensor product of n spaces of 2 dimensions, and that is not the same. The number of dimensions is very different. Sorry, properly speaking, the outputs, sorry, the output states can only be tensor products, spaces of 2 dimensions. Another model I would like to go and then we can break. We can do a break. Is the flipped model, which is something that I was very surprised when I read, and it's the following. So up to now we had data that so encoding data and then optimizing and then measure, but we can flip it around, right? We can do something like that, so that we train this, and what comes into the data is the observable data, the observable, the way we measure. And these models are more powerful than any classical model, but less powerful than completely quantum models. And the reason here is, well, relies on something that is called classical shadows. Is anyone here familiar with classical shadows? No one has ever heard of classical shadows. You have heard about. Okay. Classical shadows are a way of extracting a lot of information from the system with very few measurements. And it's summarized under the recipe of measure now, ask later. I mean, I recover a lot of data randomly, and then from this data, I can recover some properties of the circuit. Sorry, of the state. What we are doing here is, well, I train the model here, whatever. I train it once, and there is a pool of classical data that is obtained by measurement in random settings. This encoding observable that depend on X, you could transform it into a post-processing of the measurements that happens without having any information on X using the recipe of classical shadows. And through that path, you can artificially add the data without making it into the quantum circuit, but rather on how you process the measurement, and that gives you a strong state in the computational complexity theory. Also, read this paper. This Robert Huang, Kung, and Preskill predicting many properties of quantum system from very few measurements or classical shadows. It's a beautiful piece of work. It's very dense. It's like 80 pages, but it's completely worth it. Finally, I would like to go into the generalization bounds of these variational models. Generalization bounds are mathematical objects that allows us to bound the generalization error by definition, right? And these generalization bounds kind of measure the size of the function space. How do we do it? Well, you say I have a space that has some number that has some size in whatever mention, and then I can create small balls of radius epsilon, and I know how many balls fit, and I can compute how many balls fit into this space. This is called the covering number, and this is a very common technique in that sense. So You can create a set of functions that are equally equispaced, equally super important, and measure how far these points are from each other. Through mathematical foundations, we can bound generalization bounds. If you are interested in machine learning, this reference is also beautiful. It's a textbook, but you will learn everything that you will ever need to know about machine learning. Michael Wolf. And in quantum machine learning, it turns out that even though the size of available space increases exponentially, like contrary to what you may think, the generalization bounds scales only as square root t log t, where t is the number of trainable gates. This is a very strong result because that tells you that you can generalize well with a very small number of data points. This is the number of data points. Okay. As a wrap up, so variational quantum algorithms, don't forget that we're using variational methods, therefore all problems of variational quantum algorithms are inherited, and we can discuss about it if you want. Variational quantum algorithms are a subset of QML with just one data point, if you want to see it like that. Generalization and optimization have to be tackled independently. They are different problems, and they both have to give you proper results. And most importantly, there are feature maps that become a crucial. So the feature maps become a crucial aspect of QML, of variational QML, and performance critically depends on that. If you don't know how to manage that, you're out of the game automatically. There are also some. So variational quantum machine learning hasn't been so deeply studied because just variational quantum algorithms is easier, but there are ways to transfer claims from one side to another side. Okay, I will give a break here because I'm seeing dead faces, and we can continue in 30, 10:30. Sí, no me importa. Me da igual. Me da igual. Yo tenía una banda y salíamos a cantar y todo. Estoy acostumbrado a esto.
¿Cantante?
No, yo no. Back on track. Much better this one.
In fact, Adrian, before you continue, I had a question. So from what you've told us thus far, we've learned that to make variational circuits work, you need to input data multiple times. So that means that when you use quantum data, you are screwed essentially, because you can only put it at the input and not.
That's an excellent question. I mean, do you know how many hours I've spent thinking how to do that? First of all, for sure you need some. For sure you need some. Let's say some copies. But then how do you work with this with these copies? It's an open discussion. Well, I don't even think it's an open discussion. I just think that nobody knows how to do it. You could say, for example, that you have a classical quantum register, and then you control from here to some working register, so that the output, so that the first register is not contaminated with the processing. You could in principle do that, but we don't know exactly how it works. This is how the proof works, like for the mapping between reuploading and linear. But in that case, the data is classical because it's just bit strings. But we don't know how it works in general. So I'm tempted to say yes, you need copies or you're screwed directly. But we really don't know how to work with that.
Okay.
But if you're interested, we can investigate it. Okay. I'm moving to the kernel-based QML. Kernel, if you have worked on machine learning, the kernel trick is something intuitively very easy. It's just okay. It's the following: machine learning models are very good at separating data linearly, and neural networks, for example, do precisely that. There are some functions, and with this function you are kind of creating borders, linear borders for classification. The more borders you add, the more accurate you can be. So the kernel tricks allows to linearly separate data that is not separable otherwise. The kernel trick means I'm embedding my data into some other higher dimensional space, and there I can linearly separate. For example, imagine that I want to classify the circle. I know that there is no linear separation there. I could do I can do a linear separation here, linear separation here, linear separation here, and by many of them, I could, in principle, do something that is similar to a circle. Or I could say, if it's a circle, I say set equals xy plus y, x squared plus y squared, and then the circle becomes this volume, or sorry, this surface, and there I can linearly separate. I just chop it at the radius of a circle, and that's it. So this trick has been used to find quantum advantages in machine learning, because there are some kernels, there are some quantum kernels that give you quantum advantages and tell you, well, I cannot compute distances in a particular way with a classical machine, with a classical computer, because they are BQP problems, something that you cannot work with a classical computer, but quantum computers can do. And this is at the core of most of the separation, exponential separations in machine learning. So we are coming back to the problem of before. In kernel-based QML, we are utilizing a quantum computer as a kernel. So that's it. That's everything that we have to, and there were some posters yesterday on that. So you have some embedding data that comes here, some second embedding data that comes here, and I just compute the overlap between them. This is my distance. This, combined with classical methods such as support vector machines, give you a way to perform machine learning algorithms, or supervised machine learning algorithms. Because once the kernel is computed and all these functions are done, then we can just perform classification by optimizing classical parameters, and this is known. You know how to do that. So, if the quantum kernel is such that this operation cannot be classically simulated, and this is the operation that you need to perform a given learning task, you are in quantum advantage. Long story short. What is the example for that? The discrete logarithm problem that we were discussing before. So the discrete logarithm problems mathematically is just given a, b, find k such that this holds. And this problem is known to be very difficult. Well, it's known. It's believed. It's very convincingly believed that it's very difficult, but it has not been proven. So just a disclaimer. Shor's algorithm is not proven to give advantage. It's widely believed, but not proven. So how do we do it? Well, the only thing that we are doing here is we are creating a machine learning problem that is based on the discrete logarithm problems. So technically, we have a function that gives you 1 if this holds for p equals a prime, and s is a parameter that you can find. Sorry, yeah, and s is a parameter, and you just need to characterize this function. It's just a classification problem. It's just a superposition machine. You just want to linearly separate this data. The problem is that if you don't know how to linearly separate the data, it looks like this, and there is no line. There is no line that you can draw here so that to separate red points from blue points. Is there any color blind here? No. Okay, fine. Then you are following it. But if you perform the discrete logarithm kernel, it turns out that these points are transformed in a highly nonlinear way that it has inside the DLP, and now it is transformed into that, and this I can linearly separate. And this is proven up to the fact that Shor is BQP, and sorry, the Shor cannot be solved with a classical computer. It's proven that this gives you a correct solution to the learning problem. That means that this gives you quantum advantage, and it's the first ever machine learning algorithm that gives you quantum advantage for classical data. And know that there are more results since then, but almost all of them stem from either DLP problem directly or some other kind of cryptographic problem, because cryptography has inside the hidden subgroup problem, which is something that quantum computers can solve efficiently. Mainly solutions of this kind for classical data, as the only thing we know how it works is with cryptography. So the DLP problem is, well, we have already explained that, but this show rigorously a case where QML surpasses classical. Period. No questions asked here. Proof relies on Shor's, which is believed to be PQP, and this has some strong assumptions in complexity theory that are believed to be true but not proven to be true. Again, well, should I care about this? I'm starting research in quantum machine learning. Should I care about this? How relevant is this problem? Or even better, how artificial is this problem? Well, it's artificial because the solution is constructed in such a way that instead of finding the solution to a problem, I'm finding the problem for the solution that I already have. So it's highly artificial, but it's very it's very informative for the kind of techniques that you need to learn to transform computational complexity statements into learning problems. I'm trying to stay away as much as I can, so I don't want to get technical. But if you have any comment or question on computational complexity, please ask or come later and ask. This is not general. You cannot just you cannot just use this technique directly, just plug and play to solve all the learning problems. You have to work every different case. Finally, I would like to go into the expressivity of quantum kernels, which is, well, what can quantum kernel solve. And okay, so if you create quantum kernels for quantumly tractable problems, you need kernels that cannot be mimicked by a classical computer. And there is a result that tells you that for all problems that are tractable in quantum computers, there exists at least one kernel that allows for tackling a related classification problem. So you can play in both ways, so solving a problem or transform it into a learning problem. How to find this kernel in particular? Quantum kernels for kernel functions. So for kernel functions, we know that there's always exists some embedding kernel such that how to say such that you can compute this kernel with some quantum circuit. But again, it's very difficult to find the particular kernel. It's known also that under some conditions of the kernel function like that, then the embedding has to be efficient. But again, don't know how to find, we don't know how to find it. All these results are mainly existence results that tells you that there is a hope. There is some gold at the bottom of the problem, but you really have to dig hard to find it. Okay, I will move now to this linear algebra based QML. So this is an approach that obviously stands on linear algebra, and it basically most of these approaches rely on the HHL algorithm. Have you ever heard about this HHL algorithm, or has anyone not heard about it? Okay, so the HHL algorithm, HHL after Harrow, Hashimi, Lloyd, is a quantum algorithm for solving linear systems of equations. So in every case that you want to invert a matrix, you can use the HHL algorithm to invert this matrix. And there exist some techniques that to invert matrices that are more efficiently with a quantum computer than with a classical computer. There is a fine print here. Depending on the matrix, depending on the vectors that you want to invert, and depending on many things, this can be up to exponentially more efficient than inverting with a classical computer, but only in particular sets of cases, not in every case. Be very careful. There are many papers that say, hey, now I plug in HHL and I have an exponential advantage, and then HHL themselves said this is not true because you are not in the assumptions of our results. So be very careful with that. How does this go? Is, well, we just want to solve this equation. X equals a to the minus 1 to b. So how can we do it? Load matrix A, load vector V. For these 2 steps, we might need a quantum RAM, quantum random access memory, which is a device that has been theoretized but has not been built, and I doubt that you can build it. Because if you don't have that, I mean, you could do it, but you could do it without the QRAM. But if you do it without the QRAM, then you lose the advantages. There is an exponential bottleneck there. I mean, you can do it, but then it's not efficient. And then, so by applying Hamiltonian time evolution of this kind and the Fourier transform, we can extract and invert the eigenvalues, and we can do all of this within this runtime, which is very efficient because it's logarithmic in the size of the matrix, but it goes squared in the condition number of the sparsity and condition number of the matrix, right? So that means if the sparsity is n squared, as it could be, no advantage is found. And if the condition number, which is maximum eigenvalue minus over minimum eigenvalue, is very high, I mean the matrix is singular or close to singular, no advantage as well. No great advantage. What algorithms can be found here? Well, principal component analysis, or PCA. There exists a quantum version that relies on HL, quantum support vector machines, more of the same, and yeah, and those are works that contributed to the foundations of the field of how to think of quantum machine learning. I highly recommend these two papers, and there's another one by the same authors. So it's Lloyd, Mosseni, Reventhrust in permutations of order. They around 2014 they put out a couple of papers of this in this topic, and they are very interesting. So very foundational. And I would like to go also in a proposal that appeared, I think it was 2016, of quantum recommendation systems, and it will become apparent why I'm interested in quantum recommendation systems. So these systems are something that are widely used in those times because they give advice to users for purchases. So Amazon and Netflix are giving recommendations every time. If you ever go to the Netflix account of some other person, that Netflix looks different than your Netflix, and the reason is the recommendation system. So they function very well under some assumptions that happen to be very accurate. In particular, they assume low rank. So most people belong to predefined types, and we can use recommendation system, and we can invert the matrices of preferences of users, leveraging the low rank assumption, which can go to HHL. And in this result, Kerenidis and Prakash said, this is an example in which quantum computers can provide an exponential advantage. This is what they said in the paper. But then, Ewing Tang happened. Has anyone heard about Ewing Tang? Ewing Tang is the villain, the hero that we needed, the hero that we didn't deserve. So Ewing Tang appeared. So Ewing Tang was 18 years old, was in Texas, and then she went to the office of Scott Aronson, complexity theorist, and said, "Hey, Scott, I would like to work with you. 18 years, end of the bachelor. I would like to work with you." And Scott was like, "Yeah, sure. Okay, come. I know that you are very clever. Take this problem and prove that the recommendation system, and prove that this problem is BQP." That means it proved that this problem cannot be solved in a classical computer. And Ewing Tang appeared sometime later and said, "You're not going to believe that, but this is absolutely doable in a classical computer." And this is the seed of what is known as Tang's dequantization. So Tang's dequantization is a series of paper that you can read here, or you can read here, when Ewing Tang, with the same techniques, systematically destroyed all the useful applications of quantum machine learning that we had up to this point. Some of them have survived, but it was full drama in the back in that time. And what is the do I have information? Yeah. So what is the you should see the memes. They're hilarious. There is a key here. So what is the Ewing Tang dequantization? So the quantization is the process of returning quantum algorithms to quantum machine, and many applications of HHL are successfully dequantized. Why? The reason is because quantum algorithms are by nature probabilistic, right? So you cannot directly compare them to the standard computational complexity theories in P. Right? I can solve this with certain probability, and this certain probability depends on the error. What happens is that Tang realized, well, we are comparing something that is deterministic and has to give you a solution with something that gives you a solution with a certain probability. If you relax this condition in the classical sense, then the quantum algorithms are still better, but only slightly. Only a polynomial advantage, no exponential advantage. This is why everything here cannot be done, what we were discussing before. you cannot simulate these circuits because HHL by definition is not simulable. But still, there are some alternative methods to that. I think that in interest of time, I'm going to skip the generative models, but if you're interested, please come. And I'm going to go directly into the learning quantum versus classical data, because this is a very interesting topic. And in my view, it might be the way to go if you want to prove usefulness of quantum machine learning. So the folklore of quantum computing says, Feynman Dixit, nature is in classical, so if you want to make a simulation of nature, you'd better make it with a quantum computer. Well, nature is in classical, so if you want to learn from nature, you better do it with a quantum machine. That will be a translation to the quantum machines, right? To quantum machine learning. So for quantum machine learning, if you want to learn a process that comes if you want to learn a process that comes from a quantum source, then you better use a quantum machine for that, in order to make QML advantageous. So can we do that? Can we obtain quantum advantage if we machine learn physical process? So this all these things, all these concepts have been, I shamelessly took them from this tutorial in QTYR24 by Robert Huang. If you ever had the chance of talking to Robert Huang or reading any of the papers, this is the guy of classical shadows. This is the one. He's genius. It's absolutely genius and absolutely nice. If you have the opportunity to learn from these papers, please do it, because they are very informative. Hard to read, but very informative. So we will have for the quantum agents and quantum learning, we will have some data that comes from a quantum source. We will have some quantum memory that we need to solve, that we need to use to store things. Could be a quantum random access memory or some other kind of device, and we need to perform the quantum computation. If we do that in particular ways, then we can prove exponential separations. So data changes the game. This is something that we have been discussing for the entire session, but I really want to insist on it. Data changes the game, because it has been proven that if you have a function of this kind, if f of x can be computed by a classical algorithm without data in general, then quantum computers are not more powerful than digital computers. And this is a very strong result. You may say, well, yeah, sure, whatever. The point is that the underlying reasoning here is the fact that if you can learn a classical function from classical data and you can compute it, it's kind of there is not a brutal overhead, because if I can learn from data, then that means that I could generate this data classically, and that has a polynomial overhead. But if I can learn this with a classical computer without data, and that means that I could generate this quantum data with a classical computer. We believe this is not true. Also, if we have data, then that means that all the effort that we would have to put in order to simulate this data or to create this data, which is exponential, we're just skipping it. So it's an oracle. It's like a gift that someone gives to me. If I can use this gift, which is precious stone, it's something very, very valuable, I can use that to learn that. That changes the game. There are some techniques, some generalization errors, which are very, very good, data instances and so on. But the important thing is that quantum data is a scarce resource that I cannot create, but I could learn from it. Yeah. But then this leaves an open question, which is how hard is to get some data from a quantum source. We can discuss on that on the classical shadows or some other ways of measuring it. In general, this is going to be very hard because tomography and simulation and quantum dynamics, and those are not easy problems. I would like to give a small flavor of how this works by giving this example. So say that I have a quantum circuit given by U and B. U and B are as complicated as you want. I don't care how complicated they are. And then I have this gate that depends on one parameter. So it doesn't matter. It doesn't matter how these things are. The only thing that I can measure here is something of this kind. Because it has to be. It cannot be more than a sign, and a sign is specified by that. So it cannot be more than that. Can I compute these coefficients? Absolutely not. I cannot do it. But if I have a quantum computer and you give me 3 measurements, only 3 measurements, each of them to fit one of the parameters, then I can learn this for every theta, which is not easy. Something that I cannot compute, but I can learn from the data. Okay, so when I want to learn about quantum data, we can prove that there are some advantages. Imagine that learning my quantum data consists in having some unknown quantum process, a channel that works like that. And we allow for 2 different settings, one with quantum computers, one with classical computers. Quantum is, we have some classical processing, physical experiments, and so on, and we can only do it sequentially. In a quantum process, we have the physical experiments that we can entangle with each other, and this entanglement changes the game. It's an absolutely difference, and you can prove, warning, maths ahead. You can prove that for this particular problem, if you want to learn properties of the channel, there are 2 cases. Case number 1, learning on average. Okay, so if there is a quantum machine learning model trained with a number of samples such that this average error is smaller than epsilon, then I have another classical machine learning such that the corresponding error in classical things is smaller than epsilon with a small overhead, a very small overhead. If instead of going to the average, I go to the worst case performance, so something like that, not average of x, but maximum of x or supremum of x, then the quantum model would need these samples to learn. The classical model needs this sample to learn. So there is exponential versus logarithmic. This is a very strong separation, and that gives you that quantum computers must be useful to learn quantum data. And this is the way where we should go in order to prove some advantages and justify why quantum computers are useful. The reason is that quantum advantage is lost in the measurements, right? And how can you do it? Well, you can depending on how you measure, you can either you need a strong effort to compute everything tomographically, or you can try to obtain less information and do it a little bit more cheap. This is where classical shadows appear. I'm a little bit short of time, so please believe me that classical shadows are very interesting. And for learning, when you want to learn from this quantum advantage, what happens is that, well, you can justify all this statement by saying that we have a quantum state and we can obtain the representation of this state in the classical shadows, and then there exist machine learning algorithms that classical machine learning algorithms that can predict data from this data taken from a quantum source, right? So any advantage in machine learning is lost in the measurement if the measurement is not properly designed. I'm finished. Sorry for being over time a bit. So the conclusions that I want to, so the take-home messages that I would like to you to uh, put in your suitcase, whenever you leave, is that quantum machine learning exists in many forms. Not all of them speak the same language. Not all of them are directly translatable to each other, and there are very different ways of thinking of them. So this lecture was intended to be an overview for different techniques, but this is far from exhaustive. And you can go to broad literatures, reviews. There are many things that you can learn. There exist a few cases where quantum advantages has been proven. So from kernels without data, and from data coming from quantum sources mainly. What else can we do is still an open question. But important to know is that quantum machine learning is in general universal, and theoretically it has to be at least as powerful as quantum computer. But this does not justify constructing a quantum machine for a quantum machine learning, because neural networks in classical computers are just too good. And they allowed us to tackle problems that were absolutely inconceivable not that far ago. The problem of quantum machine learning to me is that the enemy is just too strong. We cannot compete with ChatGPT. It works just too well. So apart from the scene question, from the scene exception, is quantum machine learning useful? Can we prove? Can we justify constructing a quantum machine to perform learning tasks, uh, and not having the obvious counter argument that, well, neural networks are just better? Are there cases like that? Can we make a quantum machine learning useful for some cases or for general purposes algorithm? That is the big question that I'm trying to answer at some point, but I don't know. I don't have a definite answer for that. That was it. Thank you very much. Thank you for the questions. Please take me now in the coffee break, and that's it. And thank you for coming, you heroes.
Adrian, for the talk. Any questions before we leave for the coffee break? I have one quick one. Can you give us a hint of what you are working on concretely right now, given the perspective that you just gave?
Yes. So something that I'm working right now is machine learning. How to explain it? So we are working in generative models that are continuous. I skip the generative models, but generative models are ways of sampling from a probability distribution without knowing the probability distribution. And this works for discrete probability distributions. I work with generative GANs, Born machines, and so on, or Boltzmann machine. But continuous ones haven't been that explored yet. So we put out a paper recently, and now we're trying to see if there's an advantage in using classical shallows for this kind of generative models. Some other things that I will work in, I would be really interested in asking is how to use variational quantum machine learning in fault tolerant regimes, because the near term computing is more and more doubted to be useful at some point. What can we do to learn, for example, problems from physics, from many body physics? The reason to use variational is that in neural networks, parameters have been the key ingredient to make them useful. Can we export that? That would be the goal.
Oh, okay. Anything else? Okay, in that case, I won't torture you or Adrian anymore. You can go to the coffee break. Thanks.
que siempre que el mecanismo mejor. Si a mí me pones mucha información y lo he sufrido mucho, entonces prefiero dar menos y que se quede algo. Sí, sí. Claro, es que es 1 hora y media. Es que mantener una atención.
Muy bien toda la introducción. Que yo creo que se hubiera beneficiado para llevarse una idea de lo que es el campo.
Que me mato. Vale.
Es que elegir entre a Juan o
O ambas. Nosotros
yo Jesús te recomiendo que te pongas ahí para que el speaker te vea. Porque si no, cuando le quieras hacer una señal o...
Eh, eh, Okay, hi everyone. Welcome to the last session of oral contributions. Now is the turn of Bea Polo, which is presenting us non-Gaussianity for continuous variable quantum batteries. She works in ICFO and, well, when you want.
Okay, hi everyone, and thank you for giving me the chance to give this talk. I'm going to be presenting the work that I've been doing alongside my supervisor, Federico Centroni, on energy storage optimization in quantum systems. So to start with a definition, a quantum battery is any system in which energy can be temporarily stored by performing unitary operations on an initial state, say the ground state, such that the difference between the energies of the two final and initial states, which is called ergotropy, is what afterwards we will have available for extraction. These systems are interesting because they constitute a novel way to exploit the unique properties of quantum mechanics in order to store and deliver energy more efficiently. And also because as quantum systems start to integrate new technologies, such as in nanotechnology or large-scale networks, it is important to understand how we can process and manipulate energy within the systems. So what do we look for in a quantum battery, or what makes a good quantum battery? Well, most literature focuses on maximizing quantities such as the ergotropy that I just mentioned, or the power that we can extract from the battery. But it seems reasonable not to expect a huge amount of any of those quantities from tiny quantum particles. So what we do think quantum batteries could outperform classical batteries at are observables such as precision. So we think they could be an advantage for accuracy-related tasks, such as nanotechnology. So following this reasoning, we've defined our signal-to-noise ratio as precisely the proportion between the energy that can be extracted from the system and the accuracy or the uncertainty in the knowledge of such energy. And this will be the quantity that we'll strive to maximize. So the tool that we're going to use for optimization is a photonic-inspired continuous variable BQE type of algorithm. So I'm just going to briefly motivate this choice. First of all, why use an algorithm that is designed for implementation in photonic hardware? Basically, due to the unique properties of photons, especially their robustness to noise, their long coherence times due to the fact that they do not easily interact with each other. Also their fast transmission speed, and the fact that we can easily manipulate and individually address them. And also because there's a very natural mapping between some of the key elements in quantum optics and the components in classical machine learning. So for these reasons, our quantum batteries will be optical modes of light, which can be modeled as ensembles of n harmonic oscillators with unit frequency. So the Hamiltonian, the internal Hamiltonian with respect to which we'll calculate the energies, is the Hamiltonian of the harmonic oscillator. And why continuous variables? Well, the continuous variable framework is one in which information is encoded in the quadratures, such as position and momentum, which span continuous ranges of values. So this type of framework is especially suited for systems whose degrees of freedom have infinite dimensions, because when we simulate the systems with qubits or qubits with discrete variables, what happens is that we impose a truncation on the dimension of the Hilbert space, and this implies systematic errors that can be sometimes very significant. So yeah, in this continuous variable realm that we've chosen, states are typically divided into Gaussian and non-Gaussian. Gaussian states are the most common ones because they're simple to both in theory and experiment. And they follow Gaussian distributions, which means that they can be fully characterized by their first, their vector of means, which is usually neglected in literature, and their covariance matrix, which contains the second statistical moments of the quadrature variables. Thanks to the Bloch-Messiah theorem, the covariance matrix can be decomposed in such a way that the most general Gaussian state can be engineered by performing squeezing operations and energy-preserving operations on an initial thermal state, which is a vacuum state thermalized at some temperature T. Okay, so the restriction to the Gaussian realm has one limitation, which is that Gaussian distributions can be reproduced classically, so no genuine quantum effect can be observed with that. So if we want to obtain some quantum advantage, we need to introduce some non-Gaussianity into the system. The choice for non-Gaussian states is infinite, but we've decided, for our ansatz, we've decided to look at states that are constructed by performing successive photon additions and subtractions on an initial Gaussian state. There are various reasons for this choice, mainly because it's the simple, like photon subtractions and additions, is the simplest non-Gaussian operations that we know how to implement. It's also the most trivial light-matter interaction, and these kind of states represent an interpolation between the discrete and the continuous realms, and also an approach to universality, because any quantum state can be approximated as a polynomial in the ladder operators applied to a Gaussian state. So with this toolbox, I can now explain the algorithm that we're working on. Basically, an N-mode thermal state is input. It's also encoded in its covariance matrix. And this state undergoes some squeezing operations. The parameters are the ones in the slide. Some squeezing, and then some passive optics, which is comprised by beam splitters and phase shifters. And after the Gaussian set, then we perform some non-Gaussian operations. What I said, photon subtractions and additions, it can be either of them. And conditioned on the success of these non-Gaussian operations, we compute the expectation value of our cost function, which in our case is the signal-to-noise ratio that I mentioned before. And we classically optimize the parameters of the Gaussian set in order to obtain the optimal cost function. So now I'm going to comment on my results. The first of them is what actually justifies our optimization, because if you look at our figure of merit and you remember the spectrum of the harmonic oscillator, you'll say, well, it's always going to be Fock states that maximize the signal-to-noise ratio, since they're eigenstates of the harmonic oscillator. So what's the point in optimizing if you can just use Fock states? Well, this is true only when temperature is equals to 0. But what we found is that actually when you go to more realistic fluctuation levels for implementations, Fock states are not only suboptimal, but also the worst in terms of signal-to-noise ratio. And to prove this, what we've done is we've considered the same circuit as before, but we've done just squeezing and then no passive optics and then one photon addition. So if you think about the structure, when Z is equals to 1, like no squeezing, what you're engineering is a Fock state 1 ket, like the first Fock state, first excited state. So we've plotted the signal-to-noise ratio with respect to squeezing and the fluctuations that we add into the system. And here, and in the limit of no squeezing, which is squeezing parameter equals to 1, we have the Fock state. And we see that when temperature is very low, it does dominate the signal-to-noise ratio. But when you increase the temperature, it's actually the worst, the worst battery. So in the regime where, well, in an intermediate regime of temperature, it does make sense to optimize. And it's going to be the more squeezed states that give better performances. So once we've justified our optimization, we're going to consider the circuit with 2 modes for simplicity, and we fix the temperature at some arbitrary value of 0.5. So our second result is this. With this here, we're plotting the signal to noise ratio, the worst and best case scenarios of signal to noise ratio with respect to the squeezing factor. And well, the first take-home message here is that non-Gaussian wins. And this is a pretty obvious result in the sense that since Gaussian unitaries are within the set of general unitaries, it's normal to think that the maximum of any function within, like, just applying Gaussian unitaries is going to be less or equal than the same function applying any kind of unitaries. But what we're showing here is that this inequality is in fact strict. So the bound imposed by Gaussian unitaries is violated by non-Gaussian states for every value of squeezing. Another thing that we see here is that there exists what we call the stellar rank hierarchy. The stellar rank is a quantifier of non-Gaussianity, which in this case, in the structure that we are considering, is defined by the number of single photon operations that you need to engineer a non-Gaussian state. So what we see here is that the higher the stellar rank, the higher the signal to noise ratio. So there's this hierarchy imposed by stellar rank. So stellar rank defines precision in battery charging or energy storage. And finally, what we also notice here is that for the Gaussian and one photon subtracted states, the best and worst case scenarios overlap. But once you go to 2 photon subtractions and onwards, you have a difference between the worst and the best cases. And this is because the signal to noise ratio stops depending only on the squeezing parameter, and there emerges a dependence on the angles of the passive optic set. And more specifically, there emerges a dependence on the angle of the beam splitter, which is theta here. And this is the angular dependence. So what we wanted to, here we've plotted the signal to noise ratio for different squeezing factors as a function of the beam splitter. So what we wanted to prove is that this angular dependence, was generated or due to the entanglement that is created within the modes when you pass them through the beam splitter. And to prove this, we've used a non-Gaussian entanglement quantifier, which is called the SB criterion. It's defined like that, and the more negative it is, the more entangled the states are. It's a bipartite quantifier, bipartite entanglement quantifier. So we've plotted both quantities, the signal to noise ratio and the SB criterion, and we see that, like precisely what I just said, the more entangled states, that is the ones with less signal to noise with less SB criterion, are coincide, like the same angles appear for the states with maximum signal to noise ratio for the different squeezing parameters. So we do not have yet, we're working on that as an analytical relation that connects entanglement with the signal to noise ratio, but we do have numerical evidence that entanglement is a resource for good performance in quantum batteries. So lastly, we've done a free optimization of parameters for different modes, and we see that the stellar rank hierarchy is preserved. So like, even if you increase the amount of modes, you still have the non-Gaussianity trend, and also that batteries with more modes are promising in terms of constructing powerful and useful quantum batteries. So yeah, the conclusions are basically that non-Gaussianity wins, and entanglement is a source for good energy storage quantum devices. Thank you for listening.
Thank you very much, Bea. Now it's time for some questions.
Thanks for the talk. Do you have any way to address the work fluctuations in the procedures, or do you not deal with that?
What do you mean?
With the work fluctuations? Yes.
You mean like the noise, or?
No, I mean, when you extract work, you might have some fluctuations in the work, in the procedures, right?
Oh, when you start extracting it?
Yes.
No, we've done this like as an theoretical analysis. So we're just looking at the potential energy that is stored in the quantum battery, but we're not thinking about the procedure to extract work from the batteries, because I don't know anything about the experimental way to do that either.
Okay, but you use the 2-point measurements, right? the way you extract the work from the batteries?
Well, I guess I have no idea
You
how.
said the ergotropy, right?
What?
The ergotropy you presented at the beginning of
Yeah,
this
the
slide?
ergotropy is just it's just the potential work that could be extracted from the system. It's just the difference between the energy of the passive state that you have initially and the one that you have when you excite the state. So that's the potential work that you could be, or the potential energy that you could be obtaining from the system.
Okay, you stick to that.
Yeah.
Yeah, okay, thanks.
Next.
So thank you for your talk, Bea. I know very little about quantum batteries, so I just wanted your personal opinion about how close do you think this is from being a reality and being available?
Um, actually, I think it's quite far. So yeah, because like the goal, like the ultimate goal would be to maybe construct tiny robots to do like super high accuracy tasks with them. But at the moment, this is just like what could potentially be done with them, and like just showing that quantum could be. This is like a test bed for quantum advantage, but I don't think it's anywhere close.
Thank you.
They are far from being implemented.
Some last question or comment?
Hi, thank you for the talk. I just wanted to know, how did you make the simulations? Because sometimes when you start adding more photons, the thing can be very demanding, and
Yeah, actually, the procedure for of Gaussian adding non-Gaussianity and adding photon subtractions and additions, we sort of post-selected on clicks, in the sense that when you add or subtract a photon, there's a very little probability of success, because it depends on the reflectivity of the beam splitter that you use for the photon subtraction, and in practice it happens very not often, but we considered every time that we did a successful non-Gaussian operation, so we kind of post-selected in that sense.
okay, thank you.
Okay, let's thank again Bea. And the next one will be Pablo. Okay, the next one will be Pablo Paez, which will present us towards polynomial convergence for variational quantum algorithms using Lagrangian dynamics. So, let's go.
Yep. So first, thanks to the organizers for organizing this. So yeah, today we'll be talking about the work that I've been doing for the past 3 years, I think is now, which is studying a family of quantum algorithms, and in particular, what are known as variational quantum algorithms that Adrian has mentioned in his talk. So before starting, let me acknowledge the people that I've been working with. And yeah, let me also say that this work is highly based on some previous work by Leonid Dodgy, who was published last year. But yeah, in general, although you've already mentioned it, in a variational quantum algorithm, what you have is you have your quantum computer that say it does some kind of quantum circuit with a fixed input, which we can think of it as just being 0. So the first, yeah, 0 state. And then each gate depends on some parameter theta that we can tune, and depending on the choices that we make for our parameters theta, we get a different output state, so a different final state. And with that final state, what we do is we measure some energy with some fixed Hamiltonian. And obviously, depending on the parameters theta, we will get a different energy right after measuring. So what we want to do is we want to find a choice for theta to be for us to obtain the minimum energy after measuring the that energy, right? So how do we do that? Well, we make use of a classical computer that will tell us, we input where we are, so our final state and our choices of theta. And this classical computer tells us where to go next, so how to update our parameters theta in order to, well, again, choose new parameters theta, run the quantum computer again, so on and so forth. So one very well-known method for doing this is doing gradient descent, right? So we want to minimize a function. How can we do that? Well, we can just look at the gradient of that function. We start here, we look at the gradient here, move in the opposite direction of the gradient because we're trying to minimize. We end up here, then again, look at the gradient, so on and so forth, and hopefully we will reach the minimum of the function that we want to minimize. And there's a slight variation to this, which is the one that we study, which is known as Langevin dynamics. And in this scenario, what we have is basically the same thing. So you start somewhere, look at the gradient of your function, move in the opposite direction, but instead of just finishing here, what you do is you move randomly a bit, and then after moving randomly, which is expressed by this thing, so W would be some kind of Brownian motion, scaled by some constant beta. So yeah, we look at the gradient, move in the opposite direction, move randomly a bit, choose some point at random, and then look at the gradient at that point, so on and so forth. So yeah, there's two main issues with these kinds of algorithms. One of them is getting stuck at local minima, right? Because just if your algorithm just looks at the gradient, it doesn't really know if you're in a local minimum or a global minimum, right? So yeah, this is a problem, but one could hope that by over-parameterizing the function that you want to minimize, hopefully your local minima will become saddle points at some point by considering like a bigger and bigger dimensional system. So we won't focus in this problem. There's a few references here if you are interested in this thing. And there's, I guess, a more like fundamental kind of problem, which is baryon plateaus, which you also mentioned, which is it happens when the gradient of the function that I want to minimize becomes exponentially small with respect to the system size. So if I'm just looking at the gradient of my function and the gradient becomes exponentially small, then I need to take an exponential amount of steps in order to actually move somewhere. So that's bad in terms of convergence. So our approach to, well, what we want to do is in our work, what we want to say is kind of this issue is the only issue in the sense that if you don't have baryon plateaus, in most cases or under some mild assumptions, you will converge fast to the solution that you want to find. So our approach is kind of mathematical. So we will focus on, say, depth-2 quantum circuits with gates acting on qubits. So just like logarithmic depth quantum circuits. And then I said in the beginning that each gate depended on some parameter theta, but in this case, what we allow for the gates to do is we allow them to change globally as long as they live in SUN. So our problem now is to minimize a function. Is to minimize a function that lives in SUN times R being the number of gates that we have in our circuit. And yeah, basically this is the function, right? I choose my gate U, and then from the initial state I evolve it and then measure the energy, and that's it. I want to minimize this function, which in general is non-convex. So this is in general a hard task to do. And yeah, how are we gonna study this? Well, by using Langevin dynamics, but in this case, it's going to be the continuous time version of it. So this is not an algorithm. This is a mathematical problem. In here, your time is continuous, so it's not in an algorithm. You've got like discrete times. In here, you don't have this. And so in this sense is where our work is highly based on this previous work. In their work, they don't do anything related to quantum computing or anything, but they try to minimize a function that lives in the sphere well, in the product of n-dimensional spheres. So kind of, yes, very similar. We in a sense we try to generalize this to SUN. And well, this thing here, I'm going to mention it in the next slide, but this thing is going to be a family of random variables indexed by the time t, and these things will tell me what to choose as my set of gates. All right. So yeah, again, so saying I get a family of random variables, and associated to each random variable, I get a distribution associated to it, so probability distribution, which goes kind of like as follows. So in the beginning, I know what my configuration is. So I know that, well, my distribution is a delta function, or a delta distribution, centered at where I am. And then as I let time go by, I will be somewhere, so my configuration will be within some region with a certain probability, because I no longer have like, I'm no longer certain where I am, because I'm using some Brownian motion in my evolution. But what I know is that if I let time go to infinity, so the limit of these distributions is what's known as the Gibbs distribution associated to and so yeah, is this any helpful at all? Because otherwise, why would be looking at this? So yeah, the first theorem says that, I'm not going to say it like very well, let's just say it fast. By tuning this parameter beta, which is the one that scales the noise, and epsilon and delta being the error, basically my Gibbs distribution, that obviously depends on this parameter beta, will find the minima of my function with a very high probability. So as I'm showing you here, my probability distribution, which is expressed by this blue region here, will be around the minima of the function with a very high probability. So yeah, that's useful. But then I guess talking about convergence, if this doesn't tell me anything about convergence, right? Because this is just a limit. So yeah, we're not talking about convergence yet. So we're interested in this thing, right? How fast does rho t converge to the distribution that we know is useful? So in order to talk about convergence, we need to define what's known as total variation distance, which is a way to express the difference between two probability measures, right? So basically, the total variation distance between two probability measures is calculated as the supremum of the absolute value of the difference of the measure that these two measures give for every measurable set. Just something. And so what we want is something like this, right? So we want to have something like the distance between rho t and nu, which is the distribution that we want, becomes exponentially small with respect to time. So there exists two constants, positive constants in this, with this aspect. And so yeah, how does one prove that we have something like this? Well, you need to use something known as logarithmic Sobolev inequalities, which I'm not going to introduce. Just if it rings a bell, that's good, and if not, it's something that exists. And if one has a logarithmic Sobolev inequality, then one has this kind of thing. So if you have a logarithmic Sobolev inequality with a constant, then you actually have what you're looking for. So this is what we try to do in our work, basically trying to prove that in our setting we have what is known as a logarithmic Sobolev inequality. And so, yeah, as I was saying in the beginning, you need to assume something, right? Because otherwise, I mean, if there were no assumptions, you would be proving something like P equals NP, because you know that training these kinds of things is NP hard in general. If you can prove that you can train them efficiently, no matter your setting, that is a bad thing. Well, I mean, depending on your perspective, but I guess you don't want to prove P equals NP. Yeah, you need to assume something like there's always a good enough escape direction from which to escape from the saddle points in general. So this is said in here. You don't really have to understand everything, but basically, if you are in a critical point X and you look at the Hessian matrix of your function that you want to minimize, basically the smallest eigenvalue of your Hessian matrix is bounded by some negative constant. So there's always a escape direction from which to keep going downwards. So yeah, and by assuming that, what we can basically prove is that, again, by tuning beta to be of order Pauli in the dimension of your manifold of SUN times R, and the constant that bounds the eigenvalues of your Hessian, then you do have a logarithmic Sobolev inequality with a constant that's polynomial in the dimension in beta and in the constant that bounds your eigenvalues. So yeah, that's it. Thank you all for listening.
Okay. Thank you very much, Pablo. Great work. Does anyone has any question or comment?
Pablo, thanks for the talk. Okay, I have mainly two questions. One, have you explored any relationship between this Langevin dynamics and optimization methods that carry some sort of inertia? Saying, are you familiar with Adam?
Not quite.
So the
yeah,
point
like different optimization algorithms.
Yeah, it's a gradient descent, but instead of looking only at the gradient at that moment, you have some inertia from the previous one, so you can kind of go over the slope. So
yeah, I think that's like something that we have in mind for like further work and stuff. But I guess the main thing is that the mathematical formalism when trying to study these things becomes like really hard. I think with Langevin dynamics, like the limit distribution is known to be the Gibbs distribution and so on and so forth. Then with different things, I guess things get a bit more complicated. So we haven't studied those, but it's definitely interesting.
And another one is maybe it's my fault, but I don't quite understand. Like, what are the assumptions of these kind of results that seem fairly good? And in particular, how are they compatible with a scenario in which you have good gradient behavior, say, but a lot of local minima?
Yeah,
So,
yeah. I mean, yeah.
I cannot find the interpretation.
Yeah. No, yeah, definitely local minima is a problem in this setting. So we're assuming that we don't have local minima. As I was saying, by overparameterization, one could hope that this doesn't exist. We have studied like some examples and we've seen some good things, but again, we haven't seen any like formal proofs for this. And in general, there's always going to be, I guess, a hard problem which has like many local minima. One could hope that maybe in general, well, maybe by overparameterization, by considering like bigger and bigger systems or whatever, hopefully one could make those things disappear, but we haven't proved anything.
Any other last question?
Thank you very much for the talk. It was super cool, and the slides were very beautiful.
Thank you.
I would like to ask you about rather of a method question, because I was very interested in this like continuous like equation of for the parameters, and I was interested in exactly how you solve them. You use like a stochastic methods for solving these equations.
Yeah, I don't think you solve them explicitly. I don't think there's very few like explicit. So there's very few like equations that can be solved explicitly. Is it? I guess it's very similar to in general like differential equations in which you can't really solve things explicitly.
Okay, so it's more like you know that it tends to a Gibbs distribution.
You only know that, and if you can prove that you have the logarithmic Sobolev inequality, which is that thing over there, then you know that you converge fast, but you don't really solve it explicitly. We don't
because it's very complicated. Okay, okay, cool. Thank you.
Okay, so thank you very much. Let's thank Pablo again.
Thank you.
And now it's the turn for Alejandro. Alejandro,
You know. Ambas.
Vale, no. Está bien. Ya puedes.
Okay, so now is the turn for Alejandro Sopena, which is presenting us photonic implementation of a quantum Mora game.
Okay.
So when you
Yeah,
want.
hi. Here I'm going to talk about an article I did in collaboration with people here at Madrid and also at Edinburgh. And the idea is to implement a quantum game with photons, the quantum Mora game. So what is the Mora game? The Mora game is a very simple-minded game, but still complex enough to be used, for example, to model financial markets. And the rules are very simple. We just need a group of people, 2 or more persons, and in each round, all the players just show a number of fingers and then say a number, trying to make a guess for the total. And then the winner of each round is the one who guesses the number correctly. Well, this game is very old. It started in Rome, in the Republic, and there is this famous sentence from Cicero that in English would be something like a worthy person is someone with whom you can play Morra in the dark, because to play Morra you need to see the fingers of the other players. And there are also a lot of different paintings from artists of different countries reproducing a round of the game. But okay, maybe you think that the Mora game is something very, very old, but indeed it is still popular today. For example, last year it was declared asset of cultural interest by the government of Aragon, and in June last year. And there is also an international competition organized typically in Italy, but also outside, organized every 5 years to play the Morra. Here we can see in the middle an example. And just to finish this introduction, I just think it's worth to mention that I discovered there is a small village in Italy called La Morra. And then in this work, I'm going to focus on the Chinos game, which is a Spanish variant of the Morra, because you can play Morra with pebbles instead of fingers. And well, in Spain, you can translate pebbles by chinas. And then from chinas, we have the Chinos game. But now, today or nowadays, instead of fingers, we use coins, which is like more modern. And just a fun fact, in the 70s in Spain, it became popular, this kind of wallet that contained coins with 2 heads, with the face of a Chinese guy. But now we know that this is not related with China, so I don't know why, but Chinos doesn't come from China. And well, we consider just the 2-player case, Alice and Bob, and each one have access to a single coin. Then in each round, each player chooses a number of coins, which can be 0 or 1, and hides them in their hands. Then Alice, that is the first player, try to make a guess. And then the same for Bob. But the thing is that Bob is the second player, and he knows Alice's guess. And his guess has to be different than Alice. Okay, so now a natural question is to think what is the best strategy, the optimal strategy. And by optimal strategy, I mean the Nash equilibrium. A Nash equilibrium is a situation in which no player should change their strategy. If they do it, then their payoff will be worst. So it is a stable strategy. And well, this is something tricky, because you can think that since Alice is the first player, maybe she has some advantage, but also Bob has more information because he knows Alice guess. So what actually happens is that Alice should play randomly, should play at random, and she has to guess always 1 coin. And Bob has to play also at random, but his guesses are different. We say that he's guessing rationally, because when he plays 0 coins, he must guess 0, but when he plays 1, he must guess 2. And in this table, we can see that following this strategy, Alice wins half of the time, and the same for Bob. And so, yeah, we see that there is a classical symmetry between Alice and Bob. And also, the thing that is relevant here is that if one wins, the other one loses. So this is a zero-sum game because the draw probability is zero. It's not possible to end in a draw. Okay, so now let's move into the quantum world. The idea here is to get some sort of quantum coins, and to break, we will see that with that we can break the symmetry between Alice and Bob. And what is the? Let me outline the idea. Now we provide Alice and Bob with a set of operators, the same set for both of them, and then they can use these operators in each round to act on a reference state that we say that has 0 coins. And at the end of the round, they produce this shard state there. And from that, measuring some quantity that will be detailed below, well, later we can extract the number of coins. These kind of ideas have been already explored in 2 papers. The first one from Francisco Guinea and Miguel Ángel Martín Delgado. They proposed to use a boson creation operator to increase the number of coins. And then there are also some other implementations with 1 qubit and 2 qubits by Daniel Centeno and Germán Sierra. But the thing with these implementations is that these are quantum versions, but they don't include the classical case in the formulation. And we want to propose a new formulation that includes naturally the quantum, well, the classical case. So in the classical case, we have 3 states: the state with 0 coins, 1 coin, and 2 coins. And then it seems natural to associate these states to the states that expand the Hilbert space of a Q-treat. And to move between these states, we have these 2 operators: the identity that adds no coin, and the X, which is like the Pauli X generalization, but for Q-treats. So we see that the X gate or X matrix adds a coin. So with these 2 operators, Alice and Bob can start adding coins to the reference state that has 0 coins. And now to compute the total number of coins of the state, we can just measure this number operator. And here we see that in these states, the number of coins is defined. We can also measure we can compute the probability of measuring n coins in one of these states. And in this case, very simple case, we see that it is just a delta because the number of coins is defined. So the probability is 1 or 0. And then, well, the winner of the game, I think, well, it's clear, is just the player whose guess matches the total number of coins that are in the state. But this implementation is very simple, but we will see that it allows, it will allow us to deform the game. So to introduce that, let me consider the discrete Fourier transform, and we can use it to relate the X matrix to the Z matrix. This is like the Pauli set, but for Q-treats. In the qubit case, we would have this. The Fourier transformation would be the Hadamard gate, just to put some context. And well, the Z gate is a diagonal matrix with a phase omega that is fixed. But now let me change the phase and put a general phase parameterized by a continuous parameter. Now I can use this new matrix that depends on theta to compute a new X that also depends on theta. And Alice and Bob can use it to add coins to the reference state. So now we have the 0 state, which is the same as before, the state of the classical case, and then the 1 and 2. These states can be written as a linear superposition of the previous states of the classical case. So now we see that here the number of coins in principle is not defined in the sense that it's a superposition. And now that we have all these states, we want to implement that with photons. And to do that, we encode the states in the polarization states of 2 photons. Here we have the states of the classical case. They are orthogonal states. So in principle, we can associate them to these other 3 states with photons. We just need 3 orthogonal states. And well, now let me go a little bit over the experiment to explain to you how to encode our states in the experiment. Here we have a source of light that will be polarized. For now, let's forget about these half-wave plates labeled by alpha 1, alpha 2, and alpha 3. And let's assume that we have a source of light from the laser. And okay, it is reflected in the first mirror. Then it arrives at this corner in this loop. And then, since it is horizontally polarized, then it is transmitted and arrives at this rectangle there. This rectangle there is a nonlinear crystal. this is the most important part of the experiment because since it is not linear, it produces parametric down conversion, which is a nonlinear process that is able to convert one photon into two photons with, well, in this case, with opposite polarization. So if we if we input a photon with horizontal polarization, then at the output we will get two photons. Of course, momentum is conserved and also the energy. With horizontal and vertical, well, the state will be horizontal polarization for the first photon and vertical for the second. And then it will arrive again to the corner of the triangle. The horizontal component will be transmitted and the vertical component will be reflected. So the vertical component will end up in the upper part of the setup and the horizontal component in the lower part. Then in this part we have well, we have some polarization beam splitter that allows us to distinguish between the horizontal and vertical polarization, and also we can count single photons. So with this, I have explained this a bit fast, but with this we can compute, well, we can measure the photons that we have in horizontal and vertical polarization. Now let's introduce these halfway plates there that I like to think that they are like single qubit gates, and with that we can have a superposition between horizontal and vertical polarization. And now we have a setup that is that depends on three parameters, so we can consider that this is a parameterized quantum state that depends on three parameters, and we can adjust the parameters to reproduce our theoretical states that we can compute acting with the X matrix. So we reframe this as an optimization problem, and we just optimize well, some metric that measures the similarity between the two states. Well, here we are using the Hellinger fidelity, but there are other metrics. Okay, and now let me discuss a bit the results. Here in the left plot, I'm showing the winning probabilities for Alice when Alice is choosing always 0 coins. I mean, no coin. And Bob is playing randomly, making his best guess. We have the classical case there in 2 pi over 3. When theta is 2 pi over 3, we recover the classical x. And well, we see that the winning probability when Alice is guessing 2 coins is 0, as expected. But when we move to theta equal to 4 pi 3, it's like the other peak there, then we see that Alice has some chances of winning by guessing 2 coins. But this in the classical case doesn't make sense because Alice has chosen 0 coins. So then classically the maximum number of coins can be 1, not 2. And also in theta equal pi, then Alice has an advantage over Bob when guessing 0 coins, because we see that her winning probability is larger than 0.5. And then what happens when Alice chooses 1 coin? There is something very interesting at theta equal pi, because we see that the best option for Alice is to guess 0 coins, but this doesn't make sense because Alice has chosen 1 coin. So then it's like, but the best option is to guess 0. And well, I have not mentioned this, but I think it's clear. The points are the experimental results, and the lines are the theoretical predictions, and we see that they agree well, quite well with the theory. Okay, and now let me go a bit more in detail about the strategies. To do that, we have to characterize a strategy. A strategy is just a set of probabilities. I mean, the probability of choosing 0 coins or one coin, and then the different guesses. For Alice, since she's the first player, we just consider that she can guess only. Well, she can make a single guess. Yeah, exactly. She can choose 0 coins with a given probability, 1 coin with another given probability, but her guess is always the same. But for Bob is different. Since Bob is the second player, we allow him to have different guesses depending on the coin, on the number of coins he chooses. And well, for example, in the left plot, we consider that both players, Alice and Bob, are playing at random, making their best guesses. And we see that Alice has always an advantage. This is different than in the classical case where we have seen there is a symmetry. And also there is a drop, there is the possibility of a draw. The draw probability is not 0. And then, well, Alice has an advantage, but she's not playing her best strategy yet. So in principle, she can improve even more her winning probability. And she do that in the middle plot. Then we see that now she's performing better. And then what happens in the third plot? Let's do the opposite. Now let's assume that Alice is playing randomly and Bob knows this, and he designs his best strategy trying to beat Alice. He's able to do that in some cases, but for others he's still not able to overcome Alice. And well, this is very interesting because even though Alice is not playing her optimal strategy, she is better than Bob in this particular case. And also something that is relevant here is that we can see that there are other Nash equilibriums apart from the classical case when playing randomly. We see here that there are 3 points that don't change between the 3 plots. The classical case, then 4 pi over 3, which is practically like the classical case, but by swapping the states of one coin and 2 coins. So yeah, we can consider that it is like the classical case, not very interesting in this case. But we see that for theta equal pi, we have also a Nash equilibrium because the point does not change. So that means that the strategy following the first plot cannot be improved. And in this case, this is a very different Nash equilibrium because Alice has a larger winning probability, and also it's possible to have a draw even in the Nash equilibrium. But yeah, let me explain better this thing about the Nash equilibrium, because we have been able to found a Nash equilibrium strategy for each value of theta. And well, in this case, we also recovered the result that the winning probability for Alice is larger, but here we have to distinguish something else. We have to distinguish between pure and mixed strategy. In a pure strategy, for example, Alice always makes the same guess independently of the number of coins she chooses, and the same for Bob. But in a mixed strategy, well, there is there are some probabilities. She can choose 1 coin or 0 coin with different probabilities. And we see that there are some cases in which it's possible to have a Nash equilibrium just with pure strategies and with a draw probability different than 0. And this is completely impossible in the classical case where the Nash equilibrium is achieved playing at random with a mixed strategy and the draw probability is 0, as we can see there. So yeah, this is all, and well, the conclusions are just the differences between the classical case. So Alice has an advantage in this deformed game. This game is a non-zero sum game because the draw probability is not 0. We have an equilibrium with pure strategies, and something that I have not commented on is that this framework allows its generalization very easily, because we can consider M players and M coins just using qubits, and this is something that we have done in the paper. So if you are interested, of course, you can read it. And yeah, I think that this is all. Thank you.
Thank you very much, Alejandro, for the nice talk. We have time for one very quick question.
Maybe it's too simple, but I don't understand what does it mean that when Alice, for example, has 0 coins and she guesses 2, she can win.
This is, I think this is here,
Yeah.
right?
Yeah,
This
there.
is the middle point in the left plot, right?
Yeah, or
Because,
well, any impossible outcome, no? So when
okay.
she guesses 0 with 1 coin.
Yes, the thing is that, for example, in the left plot, she's always choosing or playing 0 coins, and Bob is playing at random. Sometimes 0 coins, sometimes 1 coin. And then this is the winning probability for Alice when she gets 0 coins, 1 coin, and 2 coins. So suppose that Alice plays 0 coins and Bob plays 1 coin. Then Alice has to make a guess. If she guesses, in this case, 0 for theta equal pi, this is the best guess because the winning probability is larger than 0.5. So this means that Alice has an advantage over Bob here because her winning probability is larger. So this means that she will win more often than Bob. I don't know if it's clear or...
Kind of, but I think we can discuss it later. Yeah.
Okay, let's thank Alejandro again. Okay, the next one will be Adrià Lavall Mora, which and he will present us associative memory in the quantum regime. So
Thank you very much for inviting me to give this talk here. And this is the work that I've been doing in IFISC in Mallorca with my two supervisors, Roberta Zambrini and Gianluca Giorgi, and a postdoc, Liana Fiorelli. And for those who are not familiar of this concept of associative memory, it is just take a dynamical system, encode some information in it, and the idea of associative memory is that when you input some information which is corrupted or distorted from the original one that you previously stored, the dynamics of this system will correct these errors and you will be able to retrieve in the end the correct version of this state. And this concept was introduced by Hofield in 1982, where he said that any system which is dominated by a set of stable states or fixed points can be regarded as a content addressable memory. And as an example, he proposed a network of all two connected binary neurons, where each neuron can be in two states, either plus or minus one. And the dynamics is just a Markovian dynamics, which minimize the energy of the system. Then the idea is that the patterns, the information that you are storing, consist of strings of classical bits, either plus or minus one, and you encode these patterns using this Hebbian learning rule into the connections between neurons. And so, if the patterns are sufficiently orthogonal and they are less than the dimension of the system, you're guaranteed that these patterns will be minimums of the energy, will minimize the energy of the system. And so, starting from an initial state which is distorted, contains errors from the previously stored information, the dynamics eventually converts to the fixed point, to the one of the patterns, and then you're able to correct these errors. And this idea was taken to the quantum domain by many people, using very different models, from gate-based models to open quantum systems, etc. But they mainly face two challenges. One is that, as I said, the number of patterns that you can store in these systems compared to the size of this system, so the number of neurons, is limited by this classical limit, which was found by Amit. But also, since most of these models are based on these classical Hofield networks, this classical limit is also found that it limits the capacity of quantum models. And then the second challenge is that right now, since all the models that are proposed are based on classical data, so they encode patterns as strings of classical bits. So what we want to do is try to see if if we can construct a quantum associative memory that processes quantum data and therefore can allow us to improve also the storage capacity of such models. And we take a very general approach. We just consider that our system is a Hilbert space and the dynamics is governed by a completely positive CPTP map. And therefore we ask how much information can we store, how much quantum patterns, so density matrices, can we store, and how can we perform this association. And we identify three key properties. One is that the CPTP map needs to have these patterns as fixed points. Essentially, if you put the correct information into our system, we don't want that the dynamics destroy this information. So it needs to be invariant during the evolution. Second is that it needs to perform this associativity. We need to have some set of states that eventually converge during the dynamics to the correct pattern. So these initial states will be the ones that are corrupted, and the dynamics converge to the correct patterns. And finally, we impose this no mixing condition that says that no state can belong to two basins. So this is the case, for instance, in the classical version, where you have very orthogonal patterns, and so the basins of attraction are also orthogonal, or they are mostly disjoint. And then this was for the map, but now this imposes a structure in our Hilbert space, which needs to have two different parts. One is the stable subspace, which contains our patterns, our information, and one is the decaying subspace, which contains our initial conditions or the information that is corrupted. And as in these two blocks, we need to have more structure. First, in the stable part, we need to have some blocks that contain our patterns, which can be either orthogonal, patterns or non-orthogonal, which are stored in the coherence-free subspaces. And then in the decaying part, we need to have some blocks that contain these decaying states, and the map simply takes this information to the patterns. And so we see two properties that are very important. Here is that we need to have some dissipation, something that accumulates information into a subset of states. So starting from in some decaying states, you evolve into a particular set of states, and then symmetry. This is important because if you have a symmetry, you have a system which has a symmetry. For instance, an open quantum system has strong symmetry. This structure is guaranteed that you will have some blocks defined by the symmetry sector of your symmetry, and you will be able to construct these systems. And this idea, although it is very abstract, can be explained in very different scenarios. For instance, the case of autonomous quantum error correction. Here, the idea is that you codify your logical qubits as the fixed points of your system, and therefore the states with syndromes, the states that contain bit flips, are your states that will evolve into these fixed points. So therefore, your system inherently protects your logical qubits, since they are the fixed points and all information converges towards them. Then there is the case, for instance, of convolutional neural networks, where the initial layer contains all the input data. The last layer contains the classification layer, or the labels. And using control measurements, you reduce this dimension until you converge to the fixed points of this network, which are your data. And finally, an example that we tackled in the first paper that we work on is the problem of discrete-modulated quantum continuous variable quantum key distribution, where your key is encoded in symmetrically distributed coherent states. The thing is that when you send this key through a channel, these states are distorted, and you end up with a state that is not the original one that you encoded. So we use the concept of assistive memory to try to correct this information and bring back to the state that was originally encoded. And for that, we proposed a system that is an open quantum system, a driving dissipative nonlinear oscillator, which has two terms, a nonlinear driving term and a nonlinear dissipative term. And the nice property of this system is that in the steady state, which is there is only one, and has this structure, which is exactly the structure that we saw in the case of continuous variable quantum key distribution. But before the decay to steady state, we have a metastable phase, and each of the lobes in this metastable phase act as a tractor of the dynamics. So if we put in our system an initial state that again is distorted, it doesn't correspond to the patterns that we previously defined, that are these four lobes. The dynamics take this initial state towards one of the patterns, and therefore we're able to correct this information, just as we wanted for to have a system that displays associative memory. And with this system, we were able to show that we could improve the storage capacity compared to these classical models. And also in a follow-up paper, we were able to see that we can store genuine quantum states, not just classical states, with either squeezed or cut states, for instance. And most generally, we saw that with this general formulation of associative memory, we can improve the storage capacity when we give up of these classical learning rules, such as the Hebbian learning rule, and perform perfect association. But the problem that we find in the quantum formulation is that the patterns form a stable manifold, so mixtures between patterns will be preserved during the evolution. And with this, I conclude. Just thank you for your attention.
Thank you, Adra, for the very nice talk. So now it's time for questions.
Maybe I missed it, but to which data sets do you apply the techniques?
So the idea is that here you don't have a training data or a data set, you have patterns or information that you want to reconstruct. So and these patterns already configure your, you don't have a training phase, you have a configuration phase where you define the system so such that these patterns are the fixed points. And this
Okay.
Question?
First, thank you for the talk. So my question would be, say that in the fixed points that you want to basically take your data and move towards one of them, say there are two that are fairly similar. How does this decide to which one it goes in the end?
So you mean that you have two input states which are very close to each other, or that you're...
So you have an input state which has some error that you want to correct using this, and with this error, it kind of looks, it could look similar to either solution 1 or solution 2. How does this procedure choose either 1 or 2?
Well, no, in this case, since it is close to both patterns that you stored, then it will go to a mixture of both, and and classically you will convert to either one or the other, the one that is slightly more similar to it. Here, it will convert to a mixture of both, and by repeating the process, you will be able to obtain statistics and see which one was closer to it.
Thank you.
Let's thank Adri again. Pablo. So now is the turn for Pablo Viñas, which is presenting us microscopic parameterizations for gate set tomography under color phase noise. So, all is yours.
Thank you. So yeah, I'm Pablo Viñas. I'm a PhD student under the supervision of Alejandro Bermúdez, to whom I would like to thank first of all. And also I would like to thank the organizers for giving me the opportunity to present my work here today. So yeah, this work I'm presenting is about microscopic parameterizations for gate set tomography under color phase noise. And I know it's quite a long title, so let me introduce everything with a bit of detail. So on one hand, we have the quantum tomography and gate set tomography protocols, which are protocols designed to characterize the processes taking place in a quantum information processor in order to gain information about noise. And then at the same time, we have this color phase noise that we employ here in order to try to make these protocols a bit more efficient. Okay, so that's the main idea. We want to merge both things to make gate set tomography, in this case, a bit more efficient. So I will start with a brief review of quantum tomography. So the most simple protocol which falls under this category is state tomography. So state tomography is a very simple scheme in which you just have a quantum state, and you ideally would like to obtain a representation of it, let's say a density matrix, by using an informationally complete set of measurements, which is just a set which provides enough information for you to recover this state. Okay, so the maths are pretty simple, and you just can recover this target state by measuring some circuits up to some sampling noise. Okay. Well, but you could say this is fine, but you talked about gates. The title said gate set tomography, and this just recover a quantum state, and that's the reason why we're interested in process tomography. So the aim of process tomography is a bit different. We no longer are interested in recovering a quantum state, but instead we have a quantum process which transforms some input states into output states, and we would like to recover a representation of it. So yeah, the maths are a bit more involved, but nothing very difficult really. So you basically, the idea is that you go to your experimentalist of choice and you say, hey, I need to compute these circuits, and then he or she is gonna give you the output, the experimental frequencies of these circuits up to, again, some sampling noise. And with that, you are going to collect that data into a matrix or maybe a vector, depending on which representation you are working with. And then you can just perform linear inversion, and you will hopefully recover the representation of your quantum channel. Okay. This seems good, but the problem with quantum process tomography is that it is not really a self-consistent protocol. Let me explain this. So think about you trying to recover this quantum channel you are interested in, and it is subjected to some kind of noise. And usually what happens is that the initial states that you have to prepare to have informationally complete sets are obtained by rotating a reference or native state available in your device. But those rotations are usually subjected to the same kind of noise that the gate that you are trying to characterize. Okay, so you cannot consider them as perfect for a state preparation and then as faulty when you want to actually characterize them. So this is not a self-consistent protocol. And that's the reason behind the apparition of gate-set tomography. So gate-set tomography is an extension of quantum process tomography in which this issue is overcome by including those gates that are needed to prepare initial states and measurements and characterizing the whole set at once. Okay, so you no longer characterize just one process, you recover a whole set of processes plus the native state of your system and the measurement operator. And the maths are pretty similar, a bit more involved because you have a concatenation of 3 different quantum channels, but it's more or less the same thing. And well, this would seem right if it were not because of the fact that usually this gives you not physical maps. Okay, so when you perform linear inversion, the sampling noise that I mentioned leads to quantum channels that are typically not completely positive and trace preserving. And the way to solve this issue is just by not performing linear inversion at all. Okay, so instead of performing linear inversion, we just design carefully some cost function, and then during the optimization process, you can additionally impose the physical constraints so that you ensure that your maps are completely positive and trace preserving. Okay. Then that's the basics about gate-set tomography. Then you have some technicalities that I will not get into detail, but for example, there is this long sequence gate-set tomography protocol in which you do the same thing essentially, but you repeat a gate many times in order to enhance the accuracy with which you can compute your quantum map. This is not as straightforward as it sounds because you have to correctly select the gates or the combinations of them that amplify the parameters that you want to characterize when you repeat gates many times. In fact, that's called germ selection. Then there are other things such as fiducial pair reduction in order to try to reduce the number of circuits that you have to execute. And then you also have some kind of gauge redundancy with gate-set tomography. You can think about it in this way. So imagine you recovered a gate set and then you can transform it using a similarity transformation T. Then when you compute probabilities, the outcomes that you get are essentially the same. So gate sets up to a similarity transformation are equally valid and compatible with a set of data that you have recovered. But apart from that, we have made it. We can characterize the quantum information processor. So we have a method which is self-consistent, which gives you completely positive and trace preserving maps. So we have made it. Well, not really. The problem is that we can only do it at the cost of an exponentially large amount of resources. Okay, so you can do gate tomography for 1 qubit gates. You can do it for 2 qubit gates. You will not be able to do it for 3 qubit gates because this scales exponentially with the number of qubits. And this is the reason why we introduce this color phase model that I mentioned. So it's a simplified model that we employ to describe trapped ion devices. Okay, so in this model, we add to the standard driving Hamiltonian a stochastic term in which we introduce some stochastic processes accounting for both the phase noise of the laser and also the magnetic fluctuations that the qubit can face. And then what we do is work a little bit analytically in this formalism and recover some simplified process matrices which depend on some set of parameters which are reduced in comparison with the fully general approach. Okay, that's the idea. So the advantages of working with this model are, as I said, the reduced number of parameters that you need to determine in order to characterize your model. Then the gauge freedom no longer appears because you are introducing some physical knowledge into the system and you don't have this problem any longer. And then the fact that individual gates serve as amplificationally complete sets, which means that in the long sequence regime that I mentioned, you can just use simple gates and you will be sure that the parameters will be amplified when you repeat them. So those are some advantages compared to the general model. And now I will just give you some results which we made through simulations, which are following. So we performed GST with our model, and what we see is that the accuracy that you obtain when comparing to the original gate set that you use for simulations goes as 1 over square root of the number of shots that you are employing. Which agrees with the expected behavior, and also scales as 1 over depth when you go to that long sequence regime, which is also what you will expect. We just have some plateaus which come from decoherence, but that's expectable. Okay. Then we can compare when do we have enough circuits, enough information to perform gate set tomography when using our model and when using the fully general approach. So what you can see is that with our model, just with 11 different circuits, we can perform GST, which is why you appreciate that jump in accuracy. Whereas with the completely general model, you have to go much farther in the number of circuits axis. Okay, so you clearly have some savings here, which come from the reduced number of parameters that you have to determine, which also lead to a reduced number of circuits that you have to execute. And we can take advantage of that to see the differences between our model and the general one in terms of accuracy. Okay, so we can fix in any of these graphs a fixed amount of shots, which will correspond to a vertical line. And what you can see is that the green data, which is our custom GST model, performs at least 1 order of magnitude better than the general approach. So yeah, that's basically everything. I will just give some concluding remarks. The most near-term thing will be validating this model with some experimental data. Then we will also like to enlarge this analytical model to include entangling gates and reduce even further number of parameters that we have to determine. And then we could use this knowledge to perform some kind of error mitigation, for example, using probabilistic error cancellation or maybe other techniques. So that's the main idea. So thank you, everyone. And if you have any question, I will be happy to answer.
Thank you very much, Pablo, for the nice talk. So if anyone has any question, So no questions? If not, let's thank Pablo again, and we pass to the last talk of the day. Okay, so this workshop is coming to an end, and now we have the last talk of the week. We have Christian Tavares, who is talking about a variational toolbox for analog quantum simulators. So your turn, and
Okay, thank you so much. Well, first of all, I would like to start apologizing because I'm a little bit sick today, so please don't be really hard on me on the questions. And I also understand that this is the last talk of the workshop. So thank you to the organizers for organizing such a wonderful workshop. So I will try to make things and to keep things simple, just to give a glimpse of what we're doing. And if you are interested, just contact me or let me know, and we can go into further details. So just following this spirit, I would like to start just with some 3 take-home messages. So this is the thing that you need to remember. If you are interested in these things, then go on with me and listen to the talk. If not, just take these things home and we can go and take lunch. So the first thing that I would like to you to remember is that we kind of justify that combination by the combination of quantum optical analog quantum simulators with variational algorithms, we may find a path towards a practical quantum advantage in the near term or the middle term. Also, that some quantum optical platforms, such as QTYR trap ions, have these tunable long-range interactions, and we can take advantage of them. And finally, that these algorithms can be directly implemented. Okay, and there are a nice application of this tunable long range that actually goes beyond it. So with this in mind, if I can more or less convince you that these things are interesting, I would like to start motivating you a little bit what we do in particular. So I'm sure that you know what analog quantum simulators are. So these are typically devices that are able to mimic a target Hamiltonian using a controllable system. Okay, there are a plethora of analog quantum simulators right now, and people are really excited, especially regarding Readbear and so on. And this is a platform that have some really nice advantages, and probably the most important ones is that these calculations, the calculations that you can get with these devices, are typically considered to be more resilient to noise and errors, because somehow errors kind of get average, right? And this is really good because maybe we could get insights into systems, into really complicated systems without needing error correction. But on the other hand, typically the problem that you find is that you can only simulate with this kind of platforms Hamiltonians whose interactions you can directly engineer. Okay, either directly by interactions or somehow with some stroboscopic methods. But this is obviously a limitation. So the community, on the other hand, of quantum computing has been also limited by current devices, and they kind of came up with a nice idea, which are called these hybrid quantum classical algorithms, in which you use a quantum classical loop, in this case, the help of a quantum circuit with some classical minimization, to actually be able to encode your problem in a cost function and a quantum circuit and prepare a quantum circuit that actually solves the problem that you may be interested in. So for example, if you measure the expectation value of the Hamiltonian, you have the well-known variational quantum eigensolver, which kind of prepares an approximation of the ground state at the end of the circuit. So this is something really cool, and we said, okay, well, maybe we can combine this with analog quantum devices. So this kind of gets the best of the world, of both worlds somehow, because first we can have these native many-body entanglement operations that easily will provide you with this large-scale entanglement. That it's one of the main advantages of analog quantum simulators. Also, we assume that we can include some digital operations, some programmability to actually increase the tunability and the amount of states that we can prepare. And then, since we maybe are not able to prepare a universal quantum circuit that is able to deterministically give us the state that we want, we can somehow use this classical optimization loop to efficiently use the quantum resources that we have. So we can do quenches with Hamiltonians. We can encode the problem in this cost function and travel through the Hilbert space during the minimization of the cost functions to actually be able to prepare a target state that it's useful for knowing, let's say, some properties of a system. So this is not something that we have introduced. People have been thinking about these ideas a lot, and there are some really nice results in the literature. And actually, I told you this has been posed as a way to obtain a practical quantum advantage in the near future. But however, all these previous works has some limitations, mainly because they were inspired by digital quantum computing. And among others, the first one probably was, and the most striking one for us, is that they consider a fixed range of interactions that could be understood as a fixed connectivity. And this is something natural because these algorithms were mainly thought about at the beginning in superconducting devices, where at the end of the day you have the connectivity that you have. But in particular, in analog quantum simulators, you can have some tunability in the range of interactions. Okay, so maybe you can have some freedom in this connectivity. I'm sure that most of you know that, for example, trap ions have even an all-to-all connectivity. So maybe you can try to exploit this extra connectivity. And we were mainly inspired by the Wiki-QTYR system and also trap ions that have these tunable range interactions. And this was our first proposal. So we said, okay, can we find an advantage if we not only optimize the typical parameters in the circuit, but also this range of interactions? So we somehow optimize this connectivity. This is what we found in this first paper. And also, well, we found that typically these variational circuits have trainability issues in the optimization. Typically, they found local minima and so on. And maybe we figured out that maybe using these long ranges and hyperparameter, we can somehow alleviate partially some of these limitations. So let me just go briefly through the first one, and then we will go through the second one in the last part of the talk. So what we did is that, naturally inspired by Wiki-QTYR system, which showed this tunable long-range interaction under some conditions, we cannot replace this typical variational black box circuit by what we call the Wiki-QTYR ansat. Okay, I'm trying to see. Right. So in particular, our problem, our setup was that we built what we call the Wiki-QTYR ansat, combining first the free time evolution and the interaction Hamiltonian that you have when you have these quantum emitters coupled to a waveguide, right? So typically what you have is that you have an all-to-all connectivity, but the connectivity and the interaction amplitude between the quantum emitters, so the qubits in this case, decays exponentially with the distance, right? And you can tune this parameter L, right? And you can somehow with some lasers, you can actually get an tunability of the interaction range. So we let first let the system evolve under the interaction Hamiltonian. Then we add some single qubit rotations, and this is just with the objective of increasing the expressibility and increasing the amount of states that we can generate. We call this a layer. You can see that in yellow. And then we repeat these layers d times, okay, typically, and we get these d layers, right? We prepare a final state and we measure it and we try to encode and solve some problems. So in particular, the problems that we were interested in is as a really toy model were to find the ground state of different spin models at the critical point, in particular the transverse Felicity model and the XXZ model. And we compare the results with the typical state of the art ansat, the hardware efficient, the big layer, the Hamiltonian variational, and also our ansat, but without tunability in the range of interaction, but instead an infinite range, right? So the idea with this was try to find whether these tunable long-range interactions can give us an advantage in the preparation of these ground states. And in particular, we found when we took a look at the infidelity as a function of the depth, as a function of the number of layers at this critical point. This was done together with Alberto Muñoz, which is also collaborating in our group. Is that okay? There are a lot of data here, but what I want you to really look at is in particular, I think that is the most clear. The figure for the transverse Felicity model are around 2-3 layers. Okay, you can see that in that case we can prepare the ground state with even an order of magnitude advantages compared with the other ansats. Okay, with just in principle the same amount of resources. So this means that okay, we can use this long range, this tunable long range, to actually find an advantage compared with the state of the art results, and also compare with the infinite range case, which doesn't have this tunability. So it's not only the fact that we have long range interactions, but also the fact that we can tune them. Okay, and this was our first result, and we published it. We were happy, and it was nice. It was a really first approach to this problem, and in particular, we kind of conclude that this question had a positive answer. But as you may imagine, and as you may find typically when you do research, when you find the answer of a question, you kind of actually get a lot of more new open questions to solve. So in particular, what we found, and what we kind of wonder is that, okay, maybe this is fine, and this is a really first approach to the problem, but maybe there is a way to improve the classical optimization. This is the first thing that we wonder. Also, maybe the range of interaction shouldn't be treated as a regular parameter. Maybe there is a way to interpret it that is more suitable to this kind of problems and may help us, for example, to alleviate some of the limitations of these variational quantum algorithms. And also we wonder, well, okay, we have been studying a particular system, but do these results hold as we increase the size of the system? So let me just go briefly through these two ones, and then we can go to the last one. So what we first did is that we generalized the way QD answered, and we said, okay, this is fine for QD, but in particular, we're doing something more general. So what we can do is that we can generalize it to the time evolution under a long-range Hamiltonian, followed by the time evolution under a short-range Hamiltonian. So this allows us to include, obviously, with QD, but also allow us to include trap ions in the setup, and also even some proposals with mixture of ultraconductors to obtain these tunable, these long-range interactions. So with this, we kind of generalize first our playground, and then we said, okay, after this generalization, we can also generalize the protocol. So what we did in particular is that we promote the range of interactions to hyperparameters and optimize them separately. So the new protocol kind of first solve these equations of motions. Okay, this is equivalent to do a quantum natural gradient descent, which has some advantages compared with gradient descent. You can find in that images that in particular for the same setup, it finds the actual minimum much faster than vanilla gradient descent. So this is a better optimization algorithm than the simple VQE. Okay, but then we solve these equations of motions, we find the new times, we kind of get a lower energy result, and then we said, okay, this is cool. But now we can fix these interaction times and just optimize the range of interactions. So we kind of set up and tune a little bit our hyperparameters, okay? And we find a new energy slightly lower. Okay, and now we can fix this new range of interactions and repeat iteratively the solution of the equations of motions up until we find a new minimum, right? So with this new idea, we kind of exploit the tunable long range as an hyperparameter, and also are able to use these more powerful methods in the optimization of the system parameters. So I just want to show you a little bit of the results that we found with this. I also did with Jan Schneider, which helped me with the tensor network simulations at the beginning. So what we did is that, okay, we started studying we revisit the SM model for 40 spins and just 2 layers. And as you can see, the first neighbors case, okay, so the first neighbor will be, instead of having the long range interactions, just have a first neighbor interaction in the HLR Hamiltonian, okay? So in this case, okay, you can get a good result, but at the end of the day, you have just a few number of layers, a few number of parameters, so this is not really good. The same happening, we, instead of considering a tunable long range interaction, we consider a Rydberg-like decaying one with R to the 6. Again, this is almost first neighbor, so we do not get something really cool. But the things happen when we change when we consider these tunable long range interactions. So both for the exponential decay and the power law one, we can see we can get slightly better results. Okay, but what you can see here in this plot is that the optimizers soon find a local minima. This local minima it's not easy how to overcome it. And if we didn't have this tunability of the long range, we will get stuck in the local minima. That will be all. But then we can kind of re-optimize the range of interaction, kind of change the landscape of the optimization, and then get lower energies. And this is not only the good thing that we get, but we can also continue the optimization and we can get even lower energies. So we can break this local minima and get a new optimization. And continue this up until we get a slightly better result. At the end of the day, we got fidelities of around 80% for 40 spins, which is a good result, with just 4 quenches. So this is a really interesting way of kind of exploiting this tunable long range. Also, I mean, like to comment that these results hold as the fidelity as we scale the system size. But if you're interested, ask me on the questions because I don't have enough time to cover this. I think that we can also conclude that, okay, these things kind of hold as we increase the size of the system. And also would like just to comment a couple of things at the end. First, that, okay, this is something realistic, okay, we're actually doing the whole simulations, and, you know, computing the gradients may not be as easy as it may look like for this kind of systems and so on. But we can kind of somehow generalize this to stochastic methods and apply, for example, the quantum naturalist PSA, and still this advantage seems to hold. So this is something realistic that could be implemented in experiments right now. right? People are supposed to have the experimental capabilities. Also that we can adapt this protocol to implement real-time evolution. This is probably not so useful, but at the end of the day, I think that it's also a funny application. And finally, that right now we're also interested in going to more complicated systems, more complex systems like fermionic systems, in which this idea seems to still get us an advantage. And with this, just taking in mind that this is an ongoing work, and hopefully we will be on the archive soon. Just I want to go back to the take-home messages. Hopefully, I hope that I have convinced you of all of this. And with this, this is the end. So thank you so much for your attention. And if you have any questions, I'm open to answer anything.
Thank you very much, Christian. Does anyone has any question?
I'm Christian. Thanks for the talk. You were mentioning at some point that you can not have universality in these two paper states. What are the limitations? So what you cannot get?
Well, that's a really nice question, and I'm sure that maybe you know about this digital analog community that are actually making efforts to get universal devices with these analog setups. We're not interested in that because at the end of the day, what we're doing is just quenches under global Hamiltonians. So at the end of the day, the amount of tunability that we have, the amount of operations that we can do is not so hard if you think about it. At the end of the day, our global interaction is translational invariant, so we cannot distinguish between qubits. So that simply may justify just the fact that we cannot entangle two qubits at will. So that kind of limits the universality of the setup that we're considering. Of course, if you kind of ask for more things to your setup, at the end of the day, you can get the universality, but that's not something that we're interested into right now, because also getting universality implies a more complex setup, implies more resources, more physical resources, and that's not good for optimization actually.
The question is not in the direction that I want to demand universality, but rather in the direction that if you don't have universality, then you're biased towards some states and some other are absolutely impossible. So to me, the important part is not what you can get, but whether if you can get whatever you are interested in.
Yes, well,
which I think might help with the optimization and so on. This is what I want
yes,
to
yes,
understand.
indeed. Okay, I think that I understood you better now. Yes, well, in particular, if you think about what we're doing, we are exploring spin models, and we're trying to prepare the ground state of spin models using generalization of the interactions that make up these spin models. So at the end of the day, we will have an infinite number of layers. We could kind of get a trotterized adiabatic evolution starting from a product state and getting a ground state. So somehow this is a way to generalize this. So of course we have this limit expressibility, but having this in mind that at the end of the day we have like we're implementing like a limit version of an adiabatic evolution, where kind of have the heuristic guarantee that we're preparing states that are of the subset of the Hilbert space that we're interested in. So yes, indeed, maybe the problem typically when you have that you find when you have this universality, especially from the case of the Herbar efficient answer, supposed to actually be universal, is the thing that the universality also means that you have trainability issues. So typically you are interested in restricting the universality as much as you can, but still being able to prepare the states that you want, and that kind of gives you the good trade-off, and you're able to optimize things. In this case, these ansatz are supposed to do well. You can actually prove mathematically that you don't have barren plateaus, considering the Hamiltonian variational answer and also these generalizations. So this is one of the main motivations to kind of restrict this universality.
Okay, any more question or comment? If not, let's thank again.
¿Qué le pasa, tío? Mucho nada. Vale. Espera, que se ve el booty. Ya ha entrado ahí en el...
Okay, so this is coming to an end. First of all, I wanted to thank every participant and invited speaker for contributing to such a nice week. Then I wanted to also thank all the partners and the rest of the PISC organization for doing such a nice work. I want to remember you all that you can follow us on Twitter, and a big part of the workshop will be uploaded to YouTube. Also, we are looking for new young researchers in quantum technologies in Spain to join the organization. So if you are interested, don't hesitate to contact with us. And with this, I think we can conclude the workshop. So thank you, everyone, and see you next year, I hope.
Está hecho, así que ya.
Ahora viene la defensa de Alex.
Perfecto.
Creo que ahora 15, creo que 1:30. No. Master, fallamos.
Ah, porque tengo que hacer el papeleo del TFM. Pero vale, vale. ¿Ya está? Vale.
Sí, dale. Es aburrido escucharme. Algorithm. Analog protocol. Paradigm. Here we have Newtonian predictions. There's a third things taken from being a lot of that. Not atoms that are excited. State. Also, Carl Lances Python circuits to a then space a